de los grandes retos de este siglo. Su gestión exigirá cada vez más conocimiento, más tecnología, más capacidad de anticipación y, por supuesto, más digitalización. El cambio climático, el crecimiento de las grandes áreas metropolitanas, la necesidad de infraestructuras más resilientes y la presión creciente sobre los recursos hídricos nos van a obligar a gestionar sistemas cada vez más complejos. El canal de Isabel II es un magnífico ejemplo de cómo una organización puede combinar excelencia técnica, servicio público e innovación para responder a estos desafíos. Por eso es un privilegio el contar hoy con vosotros para hablar sobre este tema tan relevante para nuestra profesión y para la sociedad. La segunda razón de alegrarme mucho de veros aquí es un poco más sentimental, pero como las próximas horas vais a hablar de digitalización, sabéis mucho más que yo de inteligencia artificial y gemelos digitales, permitidme que yo dedique esto más a la parte sentimental, ¿no? Porque este año se cumple una efeméride extraordinaria, y yo diría que se cumple además dentro de 2 días, ¿no? El día 18 de junio de 1851, la reina Isabel II y el presidente del Consejo de Ministros, que Juan Bravo Murillo, ese que el nombre de la calle famosa, pues Juan Bravo Murillo, firmaban un decreto que autorizaba las obras destinadas a traer agua a Madrid desde el río Lozoya. Aquella decisión yo diría que es una de las que más ha cambiado para siempre el futuro de esta ciudad. La historia había comenzado algunos años antes. En 1848, Isabel II encargó a 2 ingenieros de esta escuela, a Juan Rafo y a Juan de Rivera, la redacción de un proyecto capaz de resolver el grave problema de abastecimiento que sufría Madrid. Rafo y Rivera diseñaron una solución extraordinariamente ambiciosa para la época, que era una presa, un canal y un sistema de distribución capaces de abastecer agua del Lozoya a una población 5 veces superior a la que tenía entonces la ciudad. Claro, cuando Bravo Murillo pues, conoció el proyecto, se volvió loco y dijo que a eso había que llevarlo a efecto, ¿no? Porque realmente era una apuesta sobre el futuro de Madrid. Hoy puede resultar difícil de imaginar, pero hace apenas 2 siglos la escasez de agua era uno de los principales problemas de la ciudad. Limitaba su crecimiento, generaba graves problemas de salubridad y comprometía su futuro como capital de España. El canal de Isabel II transformó radicalmente esa realidad. Fue uno de los sistemas de abastecimiento más avanzados de Europa y permitió a Madrid que creciera y prosperara y multiplicara no por 5, sino por hasta más de 30 veces su población, manteniendo un suministro de agua fiable y de calidad. Yo diría una de las mejores aguas que uno puede tomar en cualquier lugar del mundo. ¿Qué significa entonces el canal para la escuela? Pues me voy un poco más atrás. Esta escuela se funda en 1802 por Agustín de Betancourt y sus comienzos no son nada fáciles. Muy pronto los ingenieros de caminos fuimos considerados liberales y Fernando VII acabó cerrando la escuela y abriendo una tauromaquia. Así que podemos decir que durante años tenemos un pasado torero. Pero bromas aparte, pues los comienzos de la escuela fueron titubeantes, los ingenieros de caminos eran una especie nueva en este país, ¿no? Hasta que en 1858, que es cuando realmente se abre el canal, ¿no?, conseguimos algo que nos ganó el respeto de toda la sociedad, que era resolver el abastecimiento de agua de Madrid. Fue una obra colectiva, sin duda, pero fue una obra que estaba muy ligada a los profesores y ingenieros más brillantes que tenían aquella escuela, ¿no? Era Juan Rafo, Juan de Rivera o el propio Lucio del Valle. De alguna forma, ese éxito, ese lanzamiento del canal de Isabel II contribuyó decisivamente a consolidar el prestigio social de los ingenieros de caminos y de esta escuela. Por eso la relación entre ambas instituciones viene desde tan lejos y por eso para mí es muy simbólico que hoy, cuando estáis a puntito de celebrar vuestro 175 aniversario, pues estemos hoy aquí juntos hablando del agua. Los desafíos evidentemente son distintos, pero la misión sigue siendo la misma. En cierto modo, los compañeros de camino también seguimos siendo los mismos. La innovación entonces era construir un canal, la innovación hoy puede ser construir un gemelo digital. El objetivo continúa siendo exactamente el mismo, utilizar la ingeniería para mejorar la vida de las personas. No robo más tiempo, muchas gracias a todos los ponentes, gracias de nuevo al canal, a Juan, muchas gracias a todos por acompañarnos. Espero que disfrutéis de la jornada y desde luego bienvenidos a la escuela. Gracias.
Buenos días a todos. Gracias por querer que participemos en esta jornada que es tan importante para todos y para el canal también. Gracias a las palabras del director, que recibo con mucho cariño en lo personal, porque bueno, aquí pasé unos cuantos años de mi vida, y también en lo profesional, porque es un reconocimiento que hoy en día es difícil de encontrar, basado en la historia de una empresa como la nuestra, que efectivamente llevamos 175 años con un único propósito, que es dar el agua, recibirla y entregarla lo mejor posible al medio ambiente. Es cierto que empresas como la nuestra, y lo que no eran empresas, sino simplemente actividades, han surgido a lo largo de la historia de acuerdo con las necesidades de la sociedad. En primer lugar, había que sobrevivir, bueno, pues había que dar agua. Después, recientemente ya lo que había que dar era un agua de calidad. Surgieron los tratamientos del agua, tanto potable como el agua residual que se entraba a los ríos, ¿no? Hace poco también se incluyó la necesidad de la continuidad. Ya no podemos imaginar que sería no tener agua a las 24 horas del día. Pero lo cierto es que los desafíos son continuos y hoy en día nos encontramos en un marco terriblemente complejo que en ocasiones, más que interesante, llega a ser apasionante, pero también muy preocupante. Porque ahora mismo podemos decir que tenemos grandes desafíos que quizá podamos enmarcar dentro de 5 calidades, vamos a decirlo así. Tenemos el desafío del cambio climático que todos conocemos, pero que afecta fundamentalmente a cómo los regímenes de lluvia cambian, en general, con una menor precipitación acumulada, pero con unos eventos extremos tremendos, los cuales ya sabemos en Madrid en los últimos años cómo son, ¿no? Pero también está el reto demográfico, las necesidades de la sociedad de la vivienda no tienen ninguna solución si no se considera la entrega del agua y su recepción. Además, tenemos la necesidad de que nuestro tratamiento, nuestra operación, sea neutra energéticamente y sea sostenible medioambientalmente. Todo eso se va uniendo a los retos que ya habíamos dicho. Pero es que además necesitamos que sea sostenible económicamente. Y además, cuando en el marco regulatorio cada vez son más las exigencias que se piden y por lo tanto ese equilibrio entre todo es algo cada día más complicado, ¿no? Lo bueno de esto es que tenemos trabajo para años, los ingenieros de caminos y otras profesiones, como algún compañero que tengo aquí delante, que es industrial, pero lo dejamos hoy venir. Y esa es la parte buena, por así decirlo, ¿no? En ese marco llega la transformación digital. En el canal Isabel II, dentro de nuestro plan estratégico actual, una línea está dedicada, una de las 10 que tenemos, está dedicada a la transformación digital. Pero la transformación digital no pensada en la utilización de tecnologías así porque sí. La transformación digital hoy en día en una empresa como Canal Isabel II, que se dedica a dar un servicio público, tiene que ser una transformación que se integre en los procesos, que los cambie. Es decir, no es una herramienta, es parte intrínseca del proceso. Eso hace que toda la empresa tenga que replantear cómo actúa, cómo opera y integrar esa transformación digital en su operación habitual. Y a todo esto llega el gemelo digital. El gemelo digital quizás sea el mayor exponente de la digitalización en un sector como el nuestro, porque aúna en sí mismo los modelos hidráulicos que hemos estudiado a mano hace mucho tiempo, pero que ahora con esas herramientas podemos hacer que sean realmente sofisticados. Aúna la sensorización, el despliegue en toda la red de sensores nos permite conocer cómo está actuando en cada momento. También tiene en cuenta el estado de las infraestructuras. Hay infraestructuras que están en un nivel de envejecimiento o no que puede afectar a su comportamiento. Y además ahora ya tenemos la capacidad de predecir comportamientos. Y dentro de muy poco, con la inteligencia artificial, todos sabemos que habrá decisiones que tome la inteligencia artificial. Todo esto hace que el gemelo digital en los próximos años, ahora ya, pero en los próximos años con esta inteligencia que estaba comentando, sea el máximo exponente de la operación y el servicio del tratamiento y la entrega de agua y la recepción en un entorno urbano como el de Madrid y sus municipios colindantes. Por eso esta jornada es tan interesante. Es interesante porque podemos ver el nivel en el que estamos algunos en esa generación de gemelos digitales, pero todavía más en cómo los próximos años van a hacer que esos gemelos sean realmente el centro de atención de nuestras actividades habituales y por lo tanto de la sociedad. Por lo tanto, creo que es más que oportuna tanto en alrededor de estas infraestructuras hidráulicas como otras que me consta que ya habéis tenido también jornadas. Y por lo tanto, espero que de aquí saquemos todos buenas lecciones y además seamos optimistas en este futuro próximo que viene. Gracias de nuevo al director por sus palabras y a todos vosotros por asistir. No quiero tardar más porque estoy deseando ya ver la primera de las ponencias. Gracias.
Bueno, buenos días. Pues después de estas palabras del director de Innovación e Ingeniería de Canales de Isabel II y del director de la escuela, vamos a empezar las jornadas. La jornada va a ser en inglés y en español, dependiendo de la sesión. Así que en este momento voy a empezar a hablar en inglés. Thank you for welcoming to this event. This is a part of a series of events that we are developing on digitalization of infrastructures and cities. This one is about water infrastructures. It's an event that we were really eager to have because water engineering is very important for this school. We will have 2 sessions. The first one is focused on dams engineering, and the second on water water supply, drainage, and sewage systems. We are living a revolution in civil engineering because we have more data, more sensors, stronger connections, fast computational, more computational power, and this revolution is living everywhere. But in these cases, we will show that there are some aspects in common, for example, climate change and the use of AI. But I would like to highlight that there is a nuance, a difference between the 2 sessions, the 2 cases. In the case of dams, most of the dams, the large dams in the world, were built in the big dam era. It was between 1930 and 1970s. Most of the large dams in the world were built. And today we have very nice dams that they are aged. They are like 50 to 100 years old. And we need data science and AI to monitor the health of these infrastructures, mainly. In the case of water supply systems, we have been talking about when Canal started in Madrid, there were like 400,000 people living in Madrid region. Today, we have more than 7 million people. So this is not just about adding more pipes and more valves. This is about having more efficient, more sources, interconnected, more resilient. So the complexity that we have nowadays is much larger than just adding more pipes and valves. And we think that digitalization will bring new opportunities. So let's start with the first session on dams, but I'm not sure that the speaker is here. Yes, sorry. So we are going to start with talking about dams in Madrid, and not any dam, but El Atazar. For those that live in Madrid or have studied, you know that this is a very symbolic, a really interesting infrastructure. And for such an interesting infrastructure, we also need an excellent speaker. David Galan, please come here. He is an alumni of this school. He's also a doctor from this school, and he's the head of the dams safety department at Canal de Isabel II. And he's going to talk about this dam. I don't know if you call it a digital twin, but let me add something that I'm geotechnician, you know, and we have what we call the observational method, was a term coined by Terzaghi in the 60s of the last year. And the idea was that geotechnics is so complex that you never know how to calibrate your model at the beginning. So you do a first calibration, and then you put a lot of sensor when you are building the dam, and then you readapt your model. That is, at the end of the day, is the idea of the digital twin. And when the Atazar was designed and built, probably we didn't have internet, AI, personal computers, but they did this excellent dam, and they have been monitoring very in detail these dams, and this is what your talk is about. So the floor is yours. Thank you for accepting. Sí.
Bien, pues buenos días a todos. Muchas gracias por invitarnos tanto al canal como a mí personalmente para expresar esta ponencia. Y bueno, como bien has dicho, vamos a hablar de una de las empresas más importantes que existe en España, incluso en el mundo, el Atazar. Y bueno, mi ponencia pues la he titulado El Atazar Digital, del conocimiento clásico a la inteligencia artificial, porque es una empresa que tiene 54 años, muy carismática, y pues ha habido que tratarla, gestionarla y sobre todo monitorizarla para conocerla bien. Bueno, tengo 5 puntos en la presentación, un poco lo que es la presa, los modelos clásicos estadísticos, los modelos numéricos que tenemos implementados, los nuevos modelos híbridos basados en inteligencia artificial que estamos implementando, y luego pues hablaré de un caso práctico, cómo estos modelos nos han servido para gestionar la avenida del año 25, que bueno, pues fue el máximo histórico que tuvimos en Canal de Isabel II, y que bueno, pues las cosas se hicieron bien, y cómo estos modelos nos ayudaron a estar tranquilos con esta presa y con el resto. Bueno, estamos en el 175 aniversario y bueno, ya lo ha dicho aquí el director y Juan, entonces bueno, es un poco el fondo de pantalla que tenemos en Canal para expresar este año. Bueno, la presa del Atazar es la más importante que tenemos en Canal Isabel II, es una presa bóveda de doble curvatura de 134 metros de altura, con una capacidad de 425 hectómetros, lo que supone el 46% del almacenamiento en la Comunidad de Madrid. Canal Isabel II es la empresa que gestiona el ciclo integral del agua en toda la comunidad y aproximadamente abastecemos a 7 millones de habitantes. Es una presa, ya he dicho, carismática, muy conocida en el mundo por sus aguas, ¿no? Aguas cristalinas, muy puras, muy buenas. Sufrió una fisuración en el año 72 y, bueno, pues a 100 metros de profundidad sufrió una fisuración, como muchas presas bóveda, y a fecha actual pues es una presa que funciona muy bien, su comportamiento es muy bueno, gracias a todos los ingenieros que han pasado por el Canal de Isabel II y sobre todo a todo ese control a la que se ha sometido para tratarla con cuidado, para evitar pues, situaciones de solicitaciones extremas, ¿no? Es importante también porque seguramente sea la presa en España, vamos, seguro, que abastece en algún momento determinado a mayor número de habitantes. Estamos hablando de 7 millones de habitantes en Madrid que en algún momento pues, pueden abastecerse de la presa del Atazar. Bueno, la presa del Atazar está monitorizada, tenemos varias variables que controlamos, sobre todo nos interesan los movimientos, con péndulos, directos inversos, extensómetros para conocer deformaciones puntuales, juntas, hacemos topografía también de nivelación y colimación, tenemos GPS diferencial en diferentes puntos de la coronación y en los estribos, hacemos láser escáner, tenemos sismógrafos instalados también. Luego controlamos a la auscultación hidráulica, lo que son las filtraciones que tiene la presa, que al final es muy importante porque es una variable que nos dice un poco cómo está sangrando la presa y si hay algún problema, ¿no? Conocemos las filtraciones tanto en el cuerpo de presa, en la cimentación y en la ladera. Y luego pues controlamos presiones y temperaturas del hormigón. Tenemos un centro de control en Majadahonda donde todos estos datos llegan en tiempo real y aproximadamente en todas las presas de Madrid gestionamos unos 400.000 datos al año. Es decir, estos datos se actualizan cada 20 segundos, cada 10-20 segundos están actualizados y la auscultación también la conocemos con esa precisión. Bueno, aquí tenemos algunos planos de la presa. En la parte izquierda pues, son los 8 péndulos que tiene la presa para conocer las deformaciones. Esta presa es una presa de 134 metros de altura, con una sección muy gruesa en la parte de abajo, en lo que es la cimentación, y la amplitud de movimientos de esta presa estamos hablando de unos 35 milímetros al año, más o menos, unos 35 milímetros, en lo que es la coronación. Entonces, estos 8 péndulos nos permiten conocer en esas bases las deformaciones que tienen. Aquí a la derecha tienen el gráfico de lo que son las zonas de filtración en diferentes colores. Se recogen las filtraciones tanto de cuerpo de presa como de cimentación. Y en la parte izquierda abajo pues tenemos los extensómetros tanto de varilla para control de cimentaciones como los de control de la fisura. Y luego pues diferentes termómetros que permiten conocer, para hacer los modelos numéricos, la temperatura del hormigón. Bueno, cada día la presa se controla en tiempo real, sacamos un boletín diario y en este boletín diario nosotros digamos que determinamos las principales variables que el plan de emergencia o las principales variables que nos permiten conocer la presa y además cruzamos esos datos con unos modelos estadísticos que llevan implementados en la presa desde el año 91. Los modelos estadísticos de comportamiento son unos modelos basados en estadística que predicen, en función de esa historia de datos, cómo se va a comportar la presa. Entonces, digamos que es una forma de controlar y de estar tranquilos de lo que va a pasar, ¿no? Básicamente, la entrada de datos es nivel de embalse, carga hidrostática, temperatura ambiente y el tiempo. El paso del tiempo se ve si hay una deriva temporal o no. Y ya digo, este boletín sale todos los días a las 9 de la mañana y, pues bueno, si hay algún problema se detecta. Tenemos dos formas de medir. Por un lado, los modelos estadísticos, como ven en la parte izquierda, ahí ven el P1B1, que es el péndulo en negro, y el modelo estadístico, que se adapta muy bien en rojo, bueno, con su formulación, ya digo, a lo largo de toda la historia de la presa. Y también tenemos una serie de modelos numéricos, de modelos basados en diferencias finitas. Ahora mismo tenemos un modelo basado en el programa FLAC, que también nos permite gestionar este tipo de respuestas de la presa. Bien, los modelos clásicos son modelos estadísticos. Ya digo, tenemos datos desde el año 91 y, bueno, pues para todas las bases de la presa los tenemos implementados y se ajustan fenomenal. Aquí están las bases de los péndulos, de los 8 péndulos y, bueno, pues de alguna manera todos los días sabemos lo que va a pasar o podemos hacer una estimación. En este caso es el P1B1 radial. Desde el año 91 hasta el año 2026, el error cuadrático medio del valor real con el modelo es de 0,76 milímetros. Son modelos que, bueno, han pasado muchos ingenieros por la presa y ese conocimiento se ha ido readaptando y nosotros lo hemos actualizado en los últimos años y estamos muy contentos con este tipo de modelos. ¿Qué ocurre con este tipo de modelos estadísticos? Que si la presa presenta una situación que en el pasado no ha presentado o no ha vivido, pues suelen fallar. Pero hemos de decir que estamos muy satisfechos porque con las avenidas de estos últimos años, donde la presa ha sufrido grandes subidas de nivel, los modelos han comportado fenomenal. Bueno, ¿qué limitaciones tienen los modelos estadísticos? Pues solamente permiten predecir variables en esos puntos, ¿no? En esos puntos donde tenemos instalados los sensores, en este caso los péndulos. Para tener una predicción variable necesitamos muchos datos, muchos años. También requieren un trabajo manual para eliminar errores y, sobre todo, si hay un problema de que el modelo no se adapta a la realidad, no es muy claro qué es lo que está pasando. O sea, no sabemos muy bien qué es lo que puede pasar. En cambio, los modelos numéricos pues permiten una representación gráfica y visual muy buena. De forma global podemos conocer el comportamiento de la presa en todo el paramento. También son deterministas, por lo tanto, vamos más a los parámetros geotécnicos del terreno, de los materiales, digamos que son más físicos. Y, bueno, pues de esa manera también nos permiten conocer tenemos un conocimiento muy importante de lo que puede pasar. Tenemos una representación visual de todo. Por ejemplo, aquí ven pues, la distribución de los desplazamientos, las temperaturas, la fisuración, las cargas, la apertura de juntas, las tensiones principales. Y lo más importante de todo es que podemos estimar o predecir con este modelo situaciones futuras que la presa nunca ha vivido y poder conocer de alguna manera qué es lo que va a pasar. Digamos que esto no deja de ser un gemelo digital clásico, ¿no? Es un modelo FLAC donde pues, cualquier ingeniería lo ha hecho desde hace mucho tiempo y el futuro, pues digamos que nosotros estamos intentando esto mismo interiorizarlo para que los datos se actualicen en tiempo real con otro tipo de tecnología, otro tipo de conocimiento que va a ser el híbrido, ¿no? Los modelos híbridos basados en IA hemos hecho 2 pilotos. Bueno, hemos hecho uno realmente y vamos a empezar a otro con la subdirección de I+D+I de Canal, que ese sí que va a ser en tiempo real. El modelo híbrido que hemos hecho o que hemos materializado con una empresa pues ha sido a partir de un modelo numérico de FLAC. Hemos intentado, basado en el algoritmo LOES con Python, intentar que aprendiese un poco el comportamiento de la presa durante 3 años y los resultados que hemos tenido pues, han sido muy buenos. Bueno, el modelo LOES lo que hace, pues como cualquier filtro, cualquier modelo de inteligencia artificial, en función de una situación futura con datos parecidos en el pasado, pues intenta dar pesos a esos valores y finalmente lo que hace pues, es una estimación, en este caso pues, polinómica, para saber cómo va a comportarse la presa. Esto no es nuevo. Yo la tesis doctoral, que la hice hace 12 años, hacía algo parecido con un filtro de Kalman que digamos que lo programábamos con Excel. Pero bueno, esto hoy en día lo bueno es que hay un montón de herramientas que permiten probar y verificar que la inteligencia artificial es una herramienta muy interesante para el futuro. Bien, ¿qué hemos hecho? Pues hemos cogido 3 años nada más de la presa, hemos calibrado el modelo LOES y hemos obtenido un poco la predicción a largo plazo, a 2 años, viendo que el modelo híbrido se adaptaba fenomenal. Fíjense que en blanco pues, son las predicciones que nos da el modelo LOES, muy buena, solamente con 3 años de datos. Hemos hecho lo mismo con el modelo estadístico, en este caso era un modelo estadístico preparado únicamente con los 3 últimos años, y aquí el modelo estadístico sí fallaba más. Y lo mismo pues lo hemos hecho con el modelo numérico, con el híbrido. Entonces, bueno, esto ha sido, lo hemos presentado en varios congresos, en España, en Granada, lo hemos presentado recientemente en un congreso internacional en México. Y bueno, pues ha sido una revolución porque el mundo presístico, digamos que está esperando todos estos modelos como herramientas de ayuda a la decisión. Y este año, gracias a la subdirección de I+D+I, vamos a empezar este proyecto de monitorización en tiempo real con una empresa italiana especializada en monitorizar más de 300 puentes en Italia, que nos va a permitir, pues, con unos algoritmos de inteligencia artificial, tampoco sabemos ahora mismo cómo lo van a hacer, pero vamos a poder tener en tiempo real todos los datos de la presa y ese comportamiento. Para ellos es la primera presa que van a ejecutar como piloto, y para nosotros pues, estamos expectantes por probar todo esto, ¿no? Hay que decir que Canal Isabel II, como empresa puntera en Madrid y como empresa puntera en la gestión de presas, pues tenemos esa suerte de poder probar todas estas cosas, ¿no? Que nos permiten mirar un poco al futuro y adelantarnos, ¿no? O sea, que estamos muy, muy contentos con esta posibilidad para ver qué es lo que pasa. Y bueno, luego como práctica de todo esto, pues les explicaré un poquito la gestión de avenida, que ha sido un evento muy importante que tuvimos el pasado año. El año pasado, en el mes de marzo, pues hubo un récord de precipitaciones, hubo una aportación mensual de 500 hectómetros cúbicos en la comunidad, con un máximo diario que fue el 8 de marzo, que fue una noche inolvidable en el centro de control, porque tuvimos que estar allí por la noche pendientes, no dejaba de llover, donde se recogieron 660 hectómetros cúbicos en todas las presas. Como orden de magnitud, en la Sierra de Guadarrama, en el puerto de Cotos, cayeron en 24 horas 582 milímetros de agua, que prácticamente es lo que llueve en la Comunidad de Madrid en un año y medio. Y el 8 de marzo, pues bueno, como les digo, fue una noche fantástica. Esta es la presa del Villar. Tuvimos que abrir unos desagües que históricamente nunca se habían abierto para poder laminar la avenida. Y el salto en este mes de marzo pues supuso pasar de 72 puntos a 91 puntos en tiempo récord. Nosotros en Madrid, las presas, tenemos, como he dicho antes, 13 embalses repartidos en la Sierra de Guadarrama, y la gestión no solamente es estar pendientes de lo que nos viene de arriba. O sea, Madrid es una comunidad donde las presas son casi urbanas, están centradas en ríos, donde pues, tenemos que tener muy, muy en cuenta los caudales de afección aguas abajo. Es decir, es una variable que es muy importante para nosotros para gestionar la avenida, súper importante. De hecho, nos limita. Yo siempre explico que es como si vas con un Ferrari y te dicen que tienes que ir a 30 por hora. Pues esto es igual. Aquí nosotros podemos desaguar aguas abajo, soltar para gestionar la avenida, pero hay una variable muy importante en estos puntos, sobre todo, que son puntos de afección que hay que gestionar muy en contacto con Protección Civil. Es decir, aquí en la Comunidad de Madrid, cuando viene una avenida, se coordina muy bien con la Confederación Hidrográfica del Tajo, con Protección Civil y con los organismos que pues, están pendientes de la emergencia. Entonces, esto es importante, ¿no? No solamente dices, oye, ¿las presas pueden gestionar la avenida? Sí, pero hay que tener mucho cuidado con lo que pasa con la ordenación del territorio aguas abajo. Bueno, aquí ven un poquito el comportamiento de la presa en este día, el 8 de marzo. Fíjense cómo los péndulos pues, dieron un salto importante porque la presa subió 2 metros de altura. De repente, en ese día pues, hubo un comportamiento hacia aguas abajo, la presa se deformó hacia aguas abajo, y lo mismo pues, con el modelo numérico nos permitió conocer un poquito el comportamiento. ¿Qué ocurría en el Atazar o qué ocurría en las presas de Madrid? Pues todas las presas estaban ya laminando y el Atazar estaba todavía por llenarse, ¿no? Entonces, ¿qué ocurre? La presa de Atazar es una presa, como he dicho anteriormente, que en el año 72 sufrió una fisuración, y desde entonces lo que se ha pretendido es que las situaciones de solicitaciones no sean extremas. Mantenerlas siempre en unos niveles de llenado o de subida ascensional en función del frío, que es muy importante para la presa, que no la estresasen. Entonces, con estos modelos de comportamiento, sobre todo los estadísticos, pudimos verificar cada día, estimando con las temperaturas y con los niveles que íbamos a tener en los días siguientes, cómo iba a estar la presa, en qué situación iba a estar. Y de esa manera no estresarla, no llegar a una situación donde la presa nunca había estado y que nos obligase a activar el plan de emergencia de la presa por máximo histórico. ¿De acuerdo? Entonces, bueno, aquí ven un poquito los picos que tuvimos, sobre todo en la presa de Atazar, a ser una bóveda de hormigón. La situación más desfavorable es cuando se deforma hacia aguas abajo, que era el mes de marzo, y los fríos, las épocas frías, hacen que la presa se deforme más. Entonces, eso teníamos mucho cuidado con él. Ya digo, como siempre quisimos que la presa estuviese en su zona de confort, que no se alterase. Entonces, ese fue el protocolo que hacíamos todos los días. Todos los días intentábamos verificar, con años parecidos de tanto en temperatura como nivel de embalse, qué situación o qué predicción, qué extrapolación íbamos a tener en los días siguientes. Y era lo que hacíamos. Verificábamos temperatura, cota de embalse, y ven arriba, en negro, la deformación del año 2025 siempre iba entre medias de otras deformaciones en la que la presa ya había estado. ¿Cómo hacíamos esto? Con el modelo, con los modelos estadísticos. Hacíamos una estimación a largo plazo. Y al final, después de todo este periodo, en el mes de mayo, que fue digamos que el punto en el cual vertió la presa, conseguimos que la presa estuviese en esa zona de confort, en una situación estable y conocida por la misma. Bueno, aquí ven diferentes hitos de la presa. Año 72, inauguración. Julio del 88, primer vertido de la presa por coronación, por el aliviadero de coronación. En mayo del 91, el segundo vertido. Y bueno, pues después de 34 años conseguimos que la presa vertiese. Bueno, les he traído un pequeño vídeo aquí, simplemente para demostrar muy vistoso sobre la presa. En mayo, el 19 de mayo fue el día que vertió. Y bueno, pues digamos que era un hito, todo el mundo estaba esperando que la presa vertiese, había incluso apuestas en las redes sociales. Nosotros también, como trabajadores del canal, pues queríamos, ¿no? Hay que decir que una vez que ha vertido, pues hemos quedado un poco ahí ya, después del reto, un poco vacíos, ¿no? Pero bueno. Y nada más, era lo que quería explicarles. Quedan invitados ustedes, los que no conozcan la presa, a visitarla. Muchas gracias.
Bueno, muchas gracias, David, por una presentación tan interesante y con una infraestructura tan interesante. Cuidarla mucho porque la verdad es que es una pasada lo que tenéis ahí y que sigáis innovando y investigando con ella, ¿no? La siguiente presentación también va a ser en español. It's from Miguel Ángel Fernández Centeno. He's one of the founders of an spin-off of this university that is called ACIS 2IN. It's a startup specialized in dams safety, and they have a strong area of working on AI applied to monitoring the dam safety. The floor is yours. Tu turno, por favor.
Bueno, pues buenos días a todos. Muchas gracias por la organización, por permitirnos contaros un poco lo que hacemos desde esta spin-off que nace del Grupo de Investigación en Seguridad de Presas y Aliviaderos de esta escuela. Y que, bueno, pues dentro de una de nuestras líneas de trabajo pues es el trabajar sobre el análisis de la auscultación de las presas. En este caso, pues vamos mediante métodos de Machine Learning para analizar el comportamiento y evaluar la seguridad. Vamos a poner primero un poco en contexto la presentación. Vamos a hablar un poco de este control de seguridad de las presas a partir de los sistemas de auscultación que veremos, bueno, no veremos, pero ya os avanzo que el canal es un referente y no todo el mundo tiene ese nivel de control sobre el análisis de los datos de explotación de las presas, ¿no? Y luego, bueno, pues vamos a ver un poco lo que estamos viendo, cómo se están plantando los gemelos digitales de presas, ¿no? Para ver un poco cómo nuestra propuesta se puede encajar en este planteamiento de modelos, ¿no? Una propuesta que lo que busca es dotar a estos modelos de un modelo analítico que permita de una manera práctica obtener conclusiones que mejoren la seguridad de la infraestructura al final, ¿no? y que lógicamente que sea acoplable a estos gemelos digitales. La situación habitual de cómo se tratan o cómo se analizan los datos de auscultación de las presas, pues bueno, es un poco diferente a la que, gracias a Dios, pues el canal tiene la posibilidad de hacer. Lo normal es que los titulares de presas pues tienen presas con cientos de aparatos instalados que generan decenas de miles de datos al año. Y para los cuales no se tiene en general una referencia, un valor de referencia, sobre todo en las situaciones habituales. Las situaciones habituales del día a día, que son las que te van a permitir, de alguna manera, adelantarte a potenciales problemas, ¿no? Es más interesante detectar un problema durante su génesis, durante su principio, que esperar a que eso se desarrolle y los síntomas sean mucho más evidentes, ¿no? Entonces, a esta falta de valores se suple pues, mediante una interpretación de esa auscultación por expertos, una interpretación que se hace de manera experta por ingenieros cualificados que le tienen que dedicar bastante tiempo a interpretar esos datos, ¿no? Estos recursos expertos, pues la mayor parte de los titulares son recursos bastante escasos, con lo cual hay que buscar la manera de optimizar esos recursos. Y esta escasez de recursos al final lo que lleva tanto trabajo o tan poco recurso, al final lo que lleva es a una limitación en la cantidad de revisiones o la frecuencia de revisión de estos datos de auscultación, este juicio, ¿no?, del comportamiento, pues se hace con menos frecuencia de la que a lo mejor fuera deseable y lo cual pues te merma un poco la capacidad de detectar de manera temprana las anomalías. En cuanto a lo que son los planteamientos de los gemelos digitales que hemos estado viendo que se están desarrollando en diferentes partes, en diferentes organismos, pues bueno, son modelos que se basan en una base, en un modelo geométrico, que es el soporte al cual se le van enlazando bases de datos, documentación de explotación, documentación de emergencia, todo tipo de documentos y de referencias útiles para la explotación de la presa. Una de estas partes son la propia auscultación. Estos modelos son capaces de leer los datos de los aparatos que monitorizan el comportamiento de la presa y estos modelos permiten ver el valor actual de cada uno de los sensores, pueden trazar unas gráficas de evolución de comportamiento temporal, relacionarlos con los umbrales, ¿no?, que puedan tener asignados en los planes de emergencia. Tienen una gran capacidad visual, ¿no?, de representar la información, pero lo que echamos un poco en falta es una capacidad de análisis, la parte que nos toca, de esos datos de auscultación, ¿no?, para ayudar a la toma de decisiones. Entonces, el objetivo de nuestra propuesta es dotar a estos gemelos digitales de ese componente, ese módulo analítico, que se basa en la generación de esos valores de referencia. Al final, para comprobar si un sensor te está indicando algo normal o anómalo, pues necesitas una referencia. Que esta valoración, esta referencia te permita de una manera automática hacer un primer análisis para detectar potenciales desviaciones con respecto a ese comportamiento esperable, ¿no? Y que a través de esta detección de desviaciones en diferentes sensores se pueda facilitar al explotador su tarea priorizando aquellas zonas de la presa, aquellos sensores. Recordad que tenemos cientos de sensores, varios cientos de sensores, pocos expertos, pues priorizarles, oye, mirad, centrarles en qué partes de la presa son las que merecen o requieren una atención más urgente que otras, ¿no? La metodología, bueno, pues es un poco conocida ya por todos. Al final tenemos muchos datos de auscultación. Lo que vamos a hacer es entrenar una serie de modelos predictivos basados en Machine Learning o basados en estadística. Son modelos que se entrenan sobre cada sensor en base a las condiciones externas que solicitan a la presa, ¿no? Las condiciones externas que no son las actuales para cada registro, sino también le damos la información de cómo ha llegado del pasado, de la evolución de esas condiciones externas. Con estos modelos lo que se hace es una predicción de los diferentes registros, a partir de las situaciones externas se predicen los valores que serían esperables para las diferentes variables y se pueden crear unas bandas de confianza, unas bandas en función del error del modelo, unas bandas en las que tú esperarías tener el valor de que mide tu sensor, ¿no? Entonces, a partir de si estos valores que realmente está recibiendo de la auscultación están dentro de esas bandas de confianza o se salen fuera, o en el caso de estos modelos que aquí aprenden, ¿no?, del comportamiento que tú les has enseñado previamente, cuando las condiciones externas se alejan de aquellas que tú le has enseñado al modelo para que aprenda, esa predicción pues pierde robustez y no nos podemos fiar de ella. Entonces, en esos casos, etiquetamos esos registros de una manera separada, ¿no?, como registros fuera de rango, por decirlo de alguna manera. Una vez que tenemos las series de cada aparato con sus datos etiquetados en función de si están o no en las bandas o si es un registro dudoso, lo que hacemos es una clasificación de cada sensor en función de la prioridad que tiene que darle el experto a la hora del análisis, ¿no? Sobre todo para liberarle de carga o centrar su carga de trabajo en los que realmente requieren más atención, ¿no? Entonces, imagino que en el futuro todo esto con la IA generativa pues tampoco también será automatizable, pero de momento yo creo que estamos en una fase anterior, ¿no?, en la que el peso del experto sigue siendo fundamental. ¿Qué tipo de modelos estamos utilizando en nuestra aplicación? Que, bueno, nos he dicho, la llamamos SmartDAM. Pues utilizamos modelos tanto estadísticos como de Machine Learning, como os he comentado, diferentes tipos de modelos, porque cada metodología, cada algoritmo pues tiene su propia idiosincrasia y te da resultados diferentes, ¿no?, que a veces se adaptan mejor a cierto tipo de comportamientos que otros. Luego también una segunda vuelta de tuerca que le damos es la combinación de esos diferentes modelos mediante un proceso de stacking para obtener un modelo de modelos, ¿no?, que nos dé una mayor precisión, una mayor robustez a nuestras predicciones, ¿no? Ya lo ha comentado David, los modelos basados en estadísticos o de Machine Learning basados en comportamientos observados aprenden lo que les enseñas, aprenden lo que los datos de entrenamiento, de la información que tienen ahí. De ahí esos problemas que tienen a la hora de extrapolar que luego comentaremos, ¿no? La clasificación esta que os comentaba, una vez que tenemos todas las bandas, todos los sensores con sus registros etiquetados en si están dentro, fuera o son dudosos, clasificamos cada sensor en 4 clases, ¿no? La clase 1 y el sensor funciona tal y como estamos esperando que lo hiciera. Una clase 2 es un sensor que, bueno, que a veces viene, a veces va, se va un poquito, es dudoso, hay que tener cuidado, hay que vigilarlo. Y luego tenemos una clase 3 que son sensores que claramente te están mostrando una desviación mantenida, sostenida y posiblemente incrementada en el tiempo, que son sensores que requieren pues, una atención un poco más urgente, ¿no?, o más urgente. Luego tenemos esa clase 0, ¿no?, sensores no clasificables. No los podemos clasificar porque la cantidad de registros que quedan en condiciones no vistas por los modelos en su periodo de entrenamiento, pues me impiden decidir si ese sensor está bien o está mal, porque no me puedo fiar de esa predicción, ¿no? Y al final, ¿qué obtenemos de cara al experto que tiene que analizar toda esa masa de información? Pues tenemos una priorización, una lista de sensores por los que tiene que empezar a trabajar y de esa manera optimizar su tiempo, ¿no?, su dedicación. Al final nos tiene que quedar que a día de hoy, por lo menos, los modelos van a proponernos cosas, pero va a ser el ingeniero el que al final tenga que tomar la decisión. Pues al final el ingeniero va a tener que trabajar sobre esos resultados. Entonces, una vez que está implantado, SmartDAM puede estar implantado en un gemelo digital o en otras aplicaciones convencionales de gestión de la auscultación, bueno, una vez implantado, le estarán llegando datos nuevos de los comportamientos y de las variables externas que están solicitando a la presa. El SmartDAM lo que va a hacer es evaluar cada uno de los registros en función de las condiciones externas, etiquetarlos, reclasificar el sensor y organizar esos sensores para pasarle al ingeniero pues una lista, un orden de prioridad a la hora de hacer sus trabajos de evaluación. Estos trabajos de evaluación, pues bueno, entendemos que también tenemos que darle y que podemos darle al ingeniero experto herramientas para facilitárselos, ¿no? Estos modelos de Machine Learning proporcionan información que puede ser útil, muy útil para este ingeniero experto a la hora de interpretar qué es lo que puede estar ocurriendo porque ese sensor está dando un comportamiento diferente al esperado, ¿no? Entre ciertas herramientas que nos proporciona SmartDAM para hacer ese análisis, bueno, los modelos de Machine Learning te permiten obtener, te puedes sacar de ellos qué variables son las que están influyendo más en el comportamiento del sensor. Otro tipo de información también muy útil es la identificación de las tendencias, de los comportamientos irreversibles del sensor, ¿no? Que está manifestando, que está recogiendo ese sensor. Y luego aparte hemos dotado la aplicación de una serie de herramientas de análisis gráfico que al final es cómo se está haciendo actualmente todo el análisis, pero vamos, intentamos darle unas funcionalidades adicionales que faciliten esta interpretación insisto, de los sensores priorizados, que son los que van a requerir más atención, ¿no? Sobre lo que queremos trabajar. Como un ejemplo simple, esto sería un piezómetro de una presa en el que nuestra aplicación, el SmartDAM, lo ha clasificado en clase 3. Un sensor, ojo con este sensor, tenéis que vigilarlo. Un sensor que, bueno, pues se ve que en la parte final de la banda se nos está yendo. Bueno, veis en la parte de entrenamiento, que es lo que queda a la izquierda de la línea roja, veis también que hay zonas que se están saliendo. Esos son las desviaciones que tienes durante la etapa de entrenamiento que se realiza mediante un proceso de cross-validation, con lo cual eso no quiere decir que el modelo esté cometiendo ese error de manera sistemática, sobre todo en zonas conocidas. Pero sí que me está cantando en la parte ya de evaluación, zona de datos que no ha visto el modelo en ningún momento, una desviación, pequeña, pero una desviación. Podemos analizar las tripas un poco de ese modelo y vemos que bueno, pues, ese modelo está realizando su predicción sobre todo en base a integraciones del nivel de embalse de 60 días. Sabemos que la respuesta de las presas no suelen ser inmediatas, o sea, no son inmediatas, y menos en un piezómetro. Llevan un tiempo, llevan una inercia. O sea, el nivel de hoy no es el que me marca la lectura del piezómetro, sino cómo ha venido evolucionando la red de filtración a lo largo de un cierto periodo derivado de las variaciones de nivel de embalse. Entonces, en este caso, lo que está diciéndome el modelo es que este piezómetro está respondiendo sobre todo a lo que ha pasado en los últimos 60 días y luego veis que tiene entre 30 y 90, son las siguientes. Bueno, pues en esa franja de inercias, ¿no? Es donde se está moviendo la red de filtración en este piezómetro. Y luego además aparece la variable tiempo. La variable tiempo es una variable que incluimos en todos los modelos precisamente para que puedan capturar esta deriva temporal, este comportamiento irreversible que no tiene una causa asociada a una variable externa de nivel de temperatura u otro tipo, ¿no? Podemos graficar, la aplicación te permite graficar series temporales, comparar todas las variables que quieras de la presa para poder trabajar ese análisis. En este caso lo que vemos es la gráfica de la media móvil del nivel de embalse de 60 días comparada con la lectura de ese piezómetro. Como vemos hay una correspondencia muy clara, ¿no? Vemos una correlación altísima, ¿no? En un análisis rápido, a lo mejor un análisis con poco tiempo de un especialista que tiene muy poco tiempo para analizar muchísimas variables, puede decir, oye, pues esto, mira, parece que el piezómetro sigue comportándose, ¿vale? Sigue siguiendo, mantiene esa correlación, ¿no? O sea, si a bote pronto, pues parece que sigue lo que viene haciendo de siempre, ¿no? Esa correlación se analiza, la vemos, efectivamente, la media móvil de 60 días es la variable que más se correlaciona con el comportamiento del piezómetro, vemos con otros niveles, podemos analizar correlaciones con cualquier otra variable. Esto nos confirma que, bueno, que el modelo se está fijando en cosas que, bueno, que tiene sentido que se fije. Y luego lo que podemos ver es esa tendencia, podemos graficar qué tendencia ha encontrado mi modelo de Machine Learning en el comportamiento de ese piezómetro. Entonces vemos que durante todo el periodo de entrenamiento, esto lo ve la mayor parte del periodo de entrenamiento, el modelo dice, oye, la respuesta a las variaciones de nivel de embalse son constantes, no me está cambiando la forma de responder del piezómetro a lo largo del tiempo. Sin embargo, cuando llega ahí en el torno de junio de 2021, esa tendencia hace una cosa rara, baja un poquito. Tengo que ir más rápido, ¿verdad? Bueno, pues voy a correr. Entonces, esa tendencia me está marcando ahí un cambio, algo raro, ¿no? Que luego puedo investigar, ¿no? Puedo hacer un gráfico de dispersión enfrentando esas medias con el nivel de embalse, les puedo dar a esos gráficos de un código de color para ordenarlos en el tiempo y vemos que esos colores claritos son los últimos registros que son los que parece que se me están saliendo de ese comportamiento que cuando los quitamos pues lo vemos mucho más alineado y mucho más habitual, ¿no? Entonces, todo este tipo de análisis le permite al especialista, al experto, sacar conclusiones. ¿Qué limitaciones tiene esto? Las que apuntaba David. La extrapolación. La extrapolación es el talón de Aquiles de estos métodos que se basan en el aprendizaje de comportamientos adquiridos. Y luego que estamos analizando el sensor. Modelos que me dan avisos sobre cada sensor a nivel individual, cuando la presa es un conjunto, ¿no? Entonces, estas debilidades, ¿no? Pues el acoplamiento de este tipo, este módulo, a un gemelo digital, pues bueno, lo que apuntaba ya David, al fin y al cabo, esto es un ejemplo de una presa que está entrenada con una serie de niveles de embalse, está un límite, cambia la política de explotación, se le permite subir un poco más, vemos que los piezómetros siguen haciendo lo que en principio tiene buena pinta, pero claro, nuestros modelos están previsiendo sobre unos niveles de embalse que no han visto jamás. Entonces, ¿qué es lo que ocurre? Esto, que es lo que os comentaba antes, no me puedo fiar de la predicción. Hay modelos que sí me lo hacen bien y modelos que no. Entonces, no me puedo fiar de la predicción en esos casos. La solución, o una posible solución que nos permitiría un gemelo digital con un modelo numérico asociado es generar datos sintéticos fuera de esos rangos de entrenamiento, guiar a los modelos hacia dónde tendrían que darme la respuesta en caso de que les estemos pidiendo que predigan en zonas no conocidas. Y luego esto lo veo todavía casi más interesante, es hacer esa integración espacial. Los avisos de esas desviaciones de comportamiento, claro, ya si las puedo integrar en un modelo geométrico y localizarlas en el espacio, me van a permitir analizar con un criterio mucho más global, holístico, el estado real de seguridad de esa presa. Que un sensor se me vaya no quiere decir que la presa tenga un problema. Que un conjunto de sensores relacionados en una zona determinada de la presa se me estén yendo de las bandas sí que puede ser un síntoma mucho más claro de que se esté desarrollando un problema. Y poco más os cuenta porque además me está yendo de tiempo. Así que esto es todo.
Muchas gracias, Miguel. Now we'll have another example of how to apply data science to dams monitoring. For those of you that are not very familiar with dams monitoring, a dam is like a patient, and we have to check many things like the blood pressure, heartbeats, the body temperature. And for that, we use several kinds of devices. We use thermometers, blood pressure meters. And in the case of dams, we have piezometers, we have inclinometers, we have traditional surveying, but we also have satellite monitoring. So it is my pleasure to introduce Álvaro Hernández. He is the CTO of another spin-off of UPM, of this school, that is called Detectia. And they are adding a new way, let's say, another way of monitoring dams movement, and also to apply data science to check that the health of the dam is well. Okay, Álvaro, the floor is yours.
Thank you very much. Good morning, everyone. I don't know how to switch to presentation. Control. Thanks a lot. So let me present this work in which we model dam deformation time series obtained with INSAR data, in which we pay special attention to the response that they have to hydraulic and thermal external factors. So first of all, let me introduce very briefly INSAR technology. This technology allows us to measure ground deformation with millimetric precision from space. And this is done by comparing different phase of radar images taken at different dates. The advantages is that we can measure, as I said, with millimeter precision. We can do historical analysis of the dam and the surrounding areas without the need of in situ instrumentation. And the coverage that we have is very dense. On the other hand, we have some limitations. There's some difficulty in measuring areas with vegetation or snow. The sensitivity in the horizontal plane in the direction north-south is very low. And if we talk about the location, the precision is about meters. Okay, nowadays we have tons of INSAR data and many sources are available to the public, they are open, but we have a lack of systematic analysis that can be applied in order to extract the most out of this information. On top of that, we have that in dams, external factors as temperature and water level can affect the deformation. So what we propose is applying systematic models that include very simple models that can be applied systematically to every infrastructure that includes these factors, thermal and hydraulic factors, which results are very easily interpretable. The models are just a combination of two contributions. So we have a part that depends on time, which is the underlying trend, and a part that depends on external factors. These two functions, the only requirement is that they are linear in their coefficients, but the examples that we are going to see, they are very simple, but we can make them more complicated, and we can assume a logarithmic dependence with respect to time, or in general, any polynomial dependence on the external factors. In Detectia, we have developed a Python package in which we implement the results of this paper in orange on the top, in which the optimal model in every INSAR time series is obtained through multiple hypothesis testing with the beam method criteria. These criteria allow us to have a fair comparison between all the models, even if they have different number of parameters, and the different models are just all the different combinations of those kinematic variables that we want to include, as thermal dependence, logarithmic behavior, dependence with time, etc. And these criteria also prioritize simplicity. That means that the algorithm is going to select always the simplest model that explains accurately the data. Before jumping into some results, let me explain in detail an example that is very intuitive. Here we have a time series, the deformation, cumulative deformation with respect to time. And this is the model that we have, a very simple one. So what we assume is that we have a linear dependence with temperature, with water level, and then the underlying trend that we want to understand separately from the effects of the external variables is just a linear trend. And we allow also a breakpoint, a change of trend at any point in the time range. So this, in this case, we don't have a breakpoint. This is the underlying trend, which is just a linear dependence. And in insert data, usually this is everything we do. And as we're going to see, if we stop here, we are going to lose a lot of information. This is the contribution of temperature to the deformation, which is basically measured temperature multiplied by a coefficient. We have the same in orange for the water level, and adding these two components up, we have this yellow line, which is the total contribution of the external factors, which again, adding it up to the previous underlying trend, give us the complete model in red. This is the color code that we are going to see later in the results, and the components and everything will look the same. Okay, so in this work, we have worked with Vado Mojón and Forata dams. Data is obtained from Copernicus program. We are using satellite Sentinel-1 data. And in the first case, the formation time series are obtained from European Ground Motion Service. And in Forata, the time series are obtained from an internal process done by Detectia. We have different time ranges, and in both we have a very sharp sudden event, which is driven by heavy rains, and this is translated into a sharp filling of the reservoir area, and we will see the effects in the deformation. Yeah, very important. For simplicity, we have aggregated insert data in these areas of interest so that we can focus on the model results more than all the available data that we have. This would be the first result, which is the deformation in the vertical axis. On the top, we are seeing the spillway, and at the bottom, the crest of the dam. In black, we have the measured deformation with INSAR. And what we can see is that deformation is better explained if we take into account the contribution of both temperature and water level factors. What we can see is that we can decouple this from the structural behavior, and what we see is that the water level affects inversely proportional to the deformation. That means that when the water level increases, the dam goes down, and the other way around with temperature. When the temperature increases, the dam in both parts of the dam goes up as well. And the most interesting feature about this result is what we have at the crest after this rapid filling in spring of 2018. Because we have a breakpoint, we have a change of trend in green, we see it. Okay, we can understand this because we assume linear dependence, the deformation, we assume linear dependence with respect to the external factors. But it can be that this linear dependence is broken if the factors present a very sharp changes, like in this case. And the model decided to include the algorithm decided to include a breakpoint in order to explain the deformation as accurate as possible. Here we have the same parts of the dam, but this time we are looking into the horizontal plane in the east-west axis. Given the orientation of the dam, we see that negative values of deformation correspond more or less to downstream direction and positive values to upstream direction. In this case, we see that only at the crest, external factors contribute to the explanation of the deformation. In the spillway, it's not necessary. Actually, it's quite stable in this axis. In this case, both temperature and water level contribute inversely proportional to the deformation, which means that when they increase, the dam moves towards downstream direction. And in this case, we don't observe any change of trend. Let's have a look now at Forata Dam. Now, this is the same axis, is east-west axis in the horizontal plane. But this time, given the orientation of the dam, positive values point more or less downstream and negative values upstream. In this case, we see that at the crest, the formation is not affected, or at least the algorithm decided not to include water level as a factor that explains the deformation. We see that temperature contributes inversely proportional. That means that when temperature increases, the dam moves in the upstream direction. And the most important feature that we see is at the end almost, which is a change of trend that coincides with a sharp event that was a heavy rain event in October of 2024, which was translated into a very rapid filling of the reservoir level. And again, we assume linear dependence with external factors, but we have this very sharp event, so maybe this linear dependence is broken. And if we take into account that we follow the simplicity principle, the algorithm have decided to include this breakpoint instead of including the breakpoint together with the water level dependence. And I think I have time. I would like to show you a different example, but this time in a web application that we have published in this platform, Destiny, which is a European initiative that pretends to build a digital twin of the Earth. And here there are many services that apply satellite data in order to build this digital twin. So our service is Momo, and it allows us to visualize and to compute models over insert time series in a very similar way as we have seen in the presentation. At Destiny, there are many services that they are all available. If you have an account, you can access the free version of each service. In our case, this free version allows you to see different use cases. And there are also some advanced features that can be done under subscription. In our case, you can have your own space and compute your own models. But let's have a look at the basic version. Sorry. Just a second. Okay, so I would like to show you Canales Dam. Here we have both axes, vertical and planimetry. In this case, this is not east-west, but it is aligned with the dam. So it is taken at 245 degrees with respect to the north, clockwise direction. Let me show you the water level dependence. Okay, so this is the measured water level in meters. And what we see here in the map is the average velocity of each insert measurement. Yes. And what we can see is that in this part of the dam, there's a non-negligible velocity towards downstream direction in blue because it's positive. And in the rest of the dam, we can see this green, more or less green, yellowish color, which means that it's stable. We can also visualize these points by the water level dependence, which is nothing but the coefficient that we have seen in the previous equation. And we can see that in this part where the points are moving towards downstream direction are more affected by the water level changes. And we can have a quick look at a point. Here we have the insert data, the insert time series. And this series, as we have seen in the presentation, has an underlying trend, which is a steady, in this case, there are no breakpoints, it's a steady trend that moves in the positive direction. That means towards downstream. It also have a water level component, which is just the water level, the measured water level multiplied by the coefficient, this blue line multiplied by a coefficient, and the complete model. And yeah, I would like to add, since we are all interested in digital twins, this is just an interface, and this interface is taking data from the TechTias database through an API, and this API is very easily it's very easy to implement, to use this API in any software. Since digital twins need all data that is available, we have done it this way so that we can be integrated at any software or any digital twin project. And it's not only an API, that is a very useful way that we can talk one machine with another machine, but we have also implemented an MCP, which is a tool that allows AI agents to interact with the API, so that we can retrieve this information with natural language through an AI agent that uses the MCP, that uses the API. And I go back to the presentation just to leave here the conclusions, and I thank you for your attention.
Thank you very much. So next, we have been talking about prediction of movements in dams, also about visualization, but digital twins are also about data information management. So the next talk is given by Lucía Pastor of ITECO and Rubén Sancho from IDEA, and they will talk about the use of BIM models in dams, y será también en español esto.
Muy buenos días. Vamos a comenzar con esta presentación. En primer lugar, agradecer a la organización que nos permiten estar aquí. Y aunque no estén presentes, pues quería dar las gracias a Enrique Moreno, Rubén Castilla y en especial a Carlos Ballesteros, porque bueno, la implicación que han tenido en este contrato ha sido muy grande y sin ellos, pues bueno, no se puede haber llegado a donde se ha llegado. La presentación está dividida en 8 apartados. Empezaremos con la introducción, veremos los objetivos, la metodología de trabajo que hemos utilizado y ya pasaremos a la parte de digitalización con la nube de puntos, modelo geométrico, modelo BIM, la plataforma simple y terminaremos con las conclusiones. La Dirección General del Agua, a partir de fondos europeos, lanzó licitó un contrato para implementar la metodología BIM en más de 150 empresas estatales, las cuales estaban distribuidas a lo largo de las principales cuencas hidrográficas españolas. Esta iniciativa, la cual estaba financiada con fondos europeos, tenía como objetivo modernizar y mejorar los procesos de operación y mantenimiento en todas las presas, siempre con la implicación de utilizar los estándares más altos de eficiencia, seguridad y sostenibilidad. El contrato salió en 8 lotes y el importe total era de más de 20 millones de euros. Los objetivos que tenemos, pues conseguir una gestión más eficiente, precisa y sostenible. ¿Con qué objetivo? Con el objetivo de modernizar y conseguir una correcta trazabilidad en todas las tareas de conservación y explotación de las presas. Para ello se requería de nuevas metodologías. Y una de estas metodologías pues, es la metodología BIM. BIM no solo es un modelo 3D, no es un modelo bonito, no solo es una geometría, sino que se le puede incorporar toda la información parametrizada que se desee de los elementos a modelar. Y no solo es eso, es una metodología de trabajo. Todos los parámetros principales que se recogen en esta metodología vienen recogidos en un documento que es el BEP, es el Plan de Ejecución BIM. En este documento se recoge la información general del contrato, los datos del mismo, objetivos y usos que va a tener el BIM en este contrato, los sistemas de clasificación, en nuestro caso de las presas, la digitalización, los criterios de digitalización de las infraestructuras que vamos a digitalizar. Va a haber una parte colaborativa que veremos un poquito con más detalle en la siguiente diapositiva. Se definen cuáles son los entregables que se van a tener, qué recursos se van a utilizar y, por supuesto, cuál es el control de calidad que se va a aplicar. Como veíamos en uno de los apartados del BEP, se dice que tiene que ser colaborativo. ¿Esto qué quiere decir? Pues que tiene que haber un entorno en el cual todos los actores del proyecto puedan colaborar en un flujo bidireccional. Además, esto nos permite que debe ser un registro único donde toda la documentación del contrato esté localizada. Esto no es algo que se haya descubierto en este contrato. Viene definido en la ISO 19650, cuyas unas de sus palabras clave son interoperabilidad y trazabilidad continua, que es lo que se buscaba en este contrato. El entorno colaborativo en el que hemos trabajado en este contrato para poder tener este flujo direccional en toda la documentación ha sido la plataforma Microsoft Teams. En ella hay equipos, canales, hay pestañas de trabajo y además hemos incorporado unas aplicaciones en las cuales facilitaba todo esto. Se trabajó con Odoo, con Ticketing para tener las consultas, o sea, los correos electrónicos desaparecen, todo va a través de esta plataforma. Además se incorporó Trimble Connect, sobre todo para el uso de intercambio de información muy pesada. Trabajamos con nubes de puntos de varios gigas, cada una de ellas, y cada presa la componían pues, 30 40 nubes de puntos. Los módulos ya eran algo menos pesados, pero bueno, también era una herramienta que nos permitía poder hacer este intercambio. Y bueno, además sí, se incorporó un roadmap en el cual la planificación de los trabajos pues, bueno, queda bien representada. Una vez hemos visto ya pues, cuál era esta metodología de trabajo colaborativa, vamos a pasar a la parte de digitalización. Esta no es viable sin una nube de puntos, y no una nube de puntos cualquiera. Tiene que ser una nube de puntos que sea capaz de representar fielmente la realidad de nuestras infraestructuras. Para ello tiene que tener una muy buena precisión y alta resolución. En el cuadro, pues bueno, pues como ejemplo, el cuerpo de presa debe tener una densidad mínima de 1000 puntos por metro cuadrado y galerías, edificaciones, sobre todo instalaciones, equipos electromecánicos, más de 10.000. Para conseguir esta nube de puntos, se realizaron unas tareas, había unos requisitos. Primero había que hacer una visita previa a cada presa. Estas visitas estaban previamente identificados todos los elementos a modelar en un documento GIS. De esta forma no se puede olvidar ninguno. Además, había que diseñar e implementar la red de bases en cada una de las presas en el caso en el que no los tuvieran. En el caso nuestro de la configuración del Júcar no estaba implementada en ninguna de ellas, por lo cual hubo que hacerlo. Y ya con ello podemos pasar a la toma de datos LIDAR. Siempre fueron datos LIDAR, la fotogrametría no se permitía, y siempre con equipos terrestres, siempre que fuera posible, con equipos terrestres. Los lugares inaccesibles ya se montaba un LIDAR aerotransportado. Lo que teníamos que escanear, pues todos los elementos que hacen que una presa sea operable. O sea, accesos, cuerpo de presa, galerías, túneles, edificaciones, instalaciones y, por supuesto, los equipos electromecánicos. Por supuesto, hay que aplicar un control de calidad. Se hacía un control topográfico en todas las nubes de puntos, incluso en el interior de las galerías. Había que realizar los alineados de todos los escaneos y en el procesado de la nube de puntos había uno de los criterios era cumplir que el solape entre las nubes, entre cada uno de los escaneos, fuera mínimo del 30%. Además, hay que hacer una limpieza de estas nubes de puntos. Pues, hay ocasiones en las que salen elementos no modelables. Pues, en la imagen de arriba pues, es uno de los operarios que están modelando, vehículos es muy habitual, y sobre todo el reflejo del agua, como en la imagen de abajo, pues bueno, son puntos que hay que eliminar. Además, estas nubes de puntos tienen un peso altísimo y por lo tanto se tuvieron que segmentar. La limitación que se estableció fueron 4,5 gigas por cada una de ellas. Una vez tenemos las nubes de puntos, ya pasamos a qué hacer con ellas. En este contrato, la finalidad de estas nubes de puntos es realizar el modelado. Como vemos en la imagen de la derecha, si una nube de puntos, los colores que se ven en azul, no los grises, son la propia nube de puntos. Si tiene muy buena calidad, pues el modelado es muchísimo más sencillo y más preciso. En la parte de la izquierda, pues bueno, vemos el modelo ya de una presa a partir de nube de puntos en Revit y en la derecha el homólogo en IFC. Aunque esto ya no forma parte de este contrato, solamente por decir las utilidades que tienen estas nubes de puntos. Tenemos unas nubes de puntos de una calidad buenísima, donde nos pueden servir para realizar inspecciones. La imagen de la izquierda es una junta de bloque de una presa. En la parte de la derecha el estado de una tubería. Incluso si las comparamos, si tenemos una nube de puntos en una fecha y antes o después otra nube de puntos de una calidad similar, la comparativa ya nos arroja las variaciones o los movimientos que han tenido. En este caso, pues es la coronación de una presa y son los movimientos con precisión milimétrica que han habido en ella. Otro caso de control de movimientos, en el de anterior una presa, y en este, bueno, se puede aplicar a cualquier infraestructura. En este caso, pues bueno, es un talud. O sea, cualquier elemento que sea susceptible de movimiento se puede hacer esta comparativa. Y nada más, pasa a Lucía.
Vale, siguiendo con el contrato de metodología BIM, una vez que tenemos la nube de puntos, el siguiente paso es generar el modelo tridimensional a partir de esta nube de puntos. La nube de puntos lo que nos da es una referencia espacial de cómo es la geometría en ese momento, en el estado actual de la presa. Entonces, a partir de ella, el objetivo es modelar cada uno de los elementos más representativos de la presa, siempre manteniendo tanto el modelo como la nube de puntos en las coordenadas reales. O sea, es muy importante mantener una correcta georreferenciación para saber exactamente la posición real de la presa. Esto luego, en fases posteriores, nos permite alimentar este modelo con otro tipo de información o utilizarlo en otro tipo de plataforma. Partiendo de esta base, se modelan todos los elementos con todas las singularidades de los mismos. Al final hay muchos elementos que tienen diferentes geometrías, tanto tan paramétricas, sino un poco más orgánicas, como son galerías excavadas en roca. Entonces esto sí que conviene ajustarse a la nube de puntos. Lo que obtenemos con el modelo geométrico ya no es únicamente la geometría, lo que obtenemos es un modelo que representa el estado actual de la presa y que es la base para la siguiente fase, que va a ser la incorporación de información para unificar en un mismo entorno digital toda la documentación y la información de la presa. Entonces, partiendo de ese modelo, como decía, el siguiente paso es la creación del modelo BIM, que es añadir toda la información relacionada con la presa para utilizarla en el control y el mantenimiento y prepararla para su operación. Entonces, el primer paso sería la recopilación de diferente documentación relacionada con la presa, como pueden ser documentos XZT, normas de explotación, informes de comportamiento. Entonces, recopilamos toda esta información, la estructuramos y parte de esta información la incorporamos al modelo mediante unos procesos automatizados. Este proceso automatizado lo que permite es eliminar el trabajo manual del técnico y hacer que la información esté mucho más homogénea. Además, gracias a una codificación como podéis ver ahí, esas son las propiedades, gracias a la codificación que tenemos para las propiedades de cada uno de los elementos, es mucho más fácil relacionar toda la información que comentaba anteriormente con las propiedades de las compuertas, de los aliviaderos, de todos los equipos. Entonces, al final, obtenemos un modelo geométrico BIM con toda la información de la presa unificada en un mismo entorno digital que le sirve al operario para poder conocer la información de históricos de mantenimiento, de operacional, de los aparatos de ocultación, etc. Además, en este contrato también, en ese contrato también hay una parte que es la creación de un informe de integración del modelo BIM con una plataforma de gestión que se llama Simpre. Esta plataforma pertenece a un contrato distinto impulsado por la Dirección General del Agua que unifica todos los diferentes módulos que veremos a continuación y también tiene un módulo donde integra los modelos BIM. Entonces, la parte del contrato de metodología BIM de integración con esta plataforma lo que hace es relacionar los elementos GIF, que es un parámetro identificador de cada uno de los elementos dentro del modelo, y que se relaciona directamente con el mismo elemento dentro de la plataforma. Esto se hace principalmente con los elementos de auscultación. Entonces, pasamos al contrato de la plataforma Simpre. Este contrato lo impulsa la Dirección General del Agua, va también a través de fondos europeos y tiene un alcance de 175 presas en 8 confederaciones hidrográficas distintas. Los objetivos de este contrato es desplegar una plataforma donde unifica toda la información para esa operación en la gestión de la seguridad de las presas, integra información de seguridad y operacional, homogeneiza los criterios de las 8 diferentes confederaciones hidrográficas y apoya la toma de decisiones en condiciones tanto ordinarias como de emergencia. Todo esto sin interrumpir en ningún momento la operación de estas presas. Y ahora voy a poner un vídeo para que veáis los diferentes módulos que tiene la plataforma. Esto sería la plataforma para acceder. Se ha creado una para cada una de las confederaciones. Lo primero que vemos es un mapa con cada una de las presas que componen esa confederación. Luego tenemos una ficha técnica de cada presa donde se recogen los datos más relevantes. Tenemos también un archivo técnico donde está estructurada toda la información de cada una de las presas, tanto el histórico como lo más reciente. Tenemos también el plan de emergencias, que tiene 3 apartados principales, uno de real, otro para simulacros y otro para entrenamientos. Tenemos el módulo de mantenimiento, donde se pueden crear los organigramas necesarios. También se pueden crear planes de trabajo, asignar tareas a ciertos usuarios. Tenemos el módulo de niveles, que lo que nos permite es conocer los caudales de salida a partir de los diferentes órganos de las presas y la opción inversa, y también permite simular avenidas. Tenemos el módulo de auscultación, que nos permite conocer todos los sensores de las presas, tanto sus valores como analizar esos mismos valores dentro de las gráficas. Aquí tenemos el módulo BIM, donde podemos conocer todos los parámetros de cada uno de los elementos de las presas. Podemos orbitar por la presa, hacer secciones, ver diferentes vistas con diferentes perspectivas. Y finalmente tenemos el gestor, que es donde administramos todos los usuarios que tienen acceso a la plataforma. Entonces aquí podemos dar de alta, dar de baja, asignar los permisos de los usuarios. Estos serían los módulos. Vale. Bueno, y ya para terminar, las conclusiones con las que nos quedamos con estos 2 contratos, en primer lugar, es que gracias a estos 2 contratos, el de metodología BIM y el de Simpre, y el de la plataforma Simpre, la Dirección General del Agua impulsa la estrategia de digitalización para las presas estatales a nivel nacional. En segundo lugar, gracias a esta metodología BIM permitimos organizar toda la documentación que anteriormente estaba recogida de forma tradicional. Entonces la organizamos, la estandarizamos y la organizamos en un entorno digital. En tercer lugar, gracias a la plataforma Simple, se centraliza toda la información, se integra la monitorización, el mantenimiento y los planes de emergencia. Y por último, al final, ya no va solo estos contratos de tener un modelo BIM o de tener una plataforma, sino que el objetivo real de todo este proceso es mejorar la seguridad y la toma de decisiones en las empresas. Muchas gracias.
Bueno, muchas gracias, and we will have the last presentation of this session. I have two news, one bad news and one good news. The bad news is that you signed it outside. It was not to control the attendance, but you were enrolling in a master program starting next year. The good news is the best executive master program on digital twins for infrastructure and cities. One of these two statements is true. Maybe you don't believe me, but we have the next presentation from Luis Madruga. He's coming from Ayesa. He's the lead of digitalization at the company. And he is one of the people that took this master program 2 years ago. And he did a capstone because one of the most valuable products of this master program is that they develop a real digital twin with a company. And he developed his capstone project on a dam. So it's a very good opportunity to show what he did, what he's doing at Ayesa, and also what we do in the master program. So thank you, Luis.
Thank you very much, Nacho. Like you said, I'm Luis Madruga. I'm gonna do a quick introduction. I'm head of digital engineering in Ayesa, and a former student for this for the masters. So we were the first cohort, how we say it, for 2 years ago. So the first thing is apologies, because I'm an architect and I come to an engineer to the engineer school talk to about dams. So sorry about that. But I lead the digital engineering department, where we lead BIM methodology, digital twins implementations, and all sorts of things that we've been talked to today. So this is the capstone project that we did 2 years ago. So it's for Dañador Dam, and we did it with the support of the Confederación Hidrográfica del Guadalquivir. And the idea was to well, first of all, I have to think. I don't know if this is this. I have to think. I didn't do it alone. This is the team that did it. David, Angel, and Ivan. They were my colleagues in the masters, and we're the ones that developed this digital twin. So the idea was to develop the concept of what could a digital twin for a dam for safety and operation management could be. We've just seen a great example of one. And I'm very happy to the very interesting presentations that we've seen today, because we did this 2 years ago, and it's as you're about to see, it's validated to the examples that we've seen today. So yeah, the main objectives that we set out for the project was to define a digitalization process of the assets, of what could we do to digitalize a dam. So what would the process be? The second one was the need to provide real-time information and for the decision-making for a dam. And the third one was to implement some predictive analytics to support this decision-making for the management of the dam. So the first step was, as we've just seen, digitalization of a built asset. So it was the process to create a digital model that represents the physical reality of the asset, the geometrical reality of the asset. Here the main objective for the BIM model was to structure the information so we could locate each element for like all the IoT or the sensorization of the dam physically within the asset. So we can have a visual layer that could help us interpret all the information associated with that element within the physical the physical reality of the dam. The second one was to develop a physical model. So the physical model, I'll talk a little bit more ahead. and also some data-based models for machine learning to do some predictive analysis. So the results, what did we ended up achieving? So the first one was data marring. So we did not have the direct connection to the information. So it wasn't live data that we were analyzing. What we did was we had an historical database that was provided by us by the Confederación del Guadalquivir. And this allows us to study the information and train the models and validate the models with that historical data. Of course, being this academic project, we couldn't have direct access to the sensitive information of the management of the dam. So with that information, we did some databases models. We had the information for aforadores, medidores de juntas, y piezometros. So all the information. Sorry, I don't know how to say it in English. And yeah, we had the information to train the models and to do some prediction behavior. In the physical model, what we did was actually the geometric information that we did to calculate the model was based off the BIM model that was updated through a point cloud, so a more up-to-date geometrical representation of the assets at that moment. And so what we did was created the physical model, calculated the results in praxis, and also then we validated it through the real data that we have accumulated with the historical data that we have access. We have seen great examples before. I'm not going to get too much into it. Yeah, so this is the result of the capstone, and at the moment that we did. And so this is the next step. So like Ignacio said, this is a collaborative process with AIESA, was a company that where I work, and that we sponsored this project. So our internal idea was to support this project as 2 years ago to define this platform. So what we ended up doing was with the data that we had at the moment, our objective was to create a system, an integrated system where we could visualize this information and support it as interface, as a system of systems, let's say it like that. So we can integrate each database to allow a better interpretation of the data that we're seeing and to support decision making. So this is the layout of the platform that we're seeing here. And so what we did is we created the platform itself, and we are working. This is something that we've started working not too much ago, to create new models based on the hydrological basin of this dam, to incorporate more information to the models that we have at the moment, information from the SAE meteorological forecast, to get more to continue to develop new models and see where we can keep taking this solution. This is a graph of the architecture that we've developed. It's a very simple architecture, just to understand. Some of these, it's a microservice based architecture. So some of them are not active, like I said. So the sensors, the broker it's not active because we're not connected directly to the data. The input for the data comes from the database. But more or less, this is the system that we have implemented right now. My idea was to show you the platform, but I'm having problem with the VPN, so security reasons, etc. I cannot access from outside our internal network. Yeah, this is a little bit explaining each one of the services that we have, a little bit of the architecture. I think it's not necessary to go through each one. It's more interesting to show you a little bit of the platform itself. So our idea was to create a very simple, very easy to use system, just as a proof of concept, to see what are the use cases that we can get from the information that we have right now, and see just to evaluate the potential for new evolutions of this system. So what could be a real use case for the digital twin? Yeah. So like I said, this is a little bit of the dashboard. I'm going to go to a video, I think, because I cannot access the platform. Yeah. So this is the initial dashboard. We have the BIM model that we can navigate We also integrated a GIS model. This is a GeoServer that we have connected online, where we have all the located every data points that we have in the dam, and that we can navigate it through the GIS. We can navigate it through the BIM model, and we can see the information, historical information associated with each of the information. So this allows us, like I said before, to associate information to the location. And also, well, this is because the services are down. Some of them are not operative. The second, then we have sorry, I'm gonna go back. So if you see up, we have 5 different models for each type of information. I'm gonna go forward. Yeah. So this is our information for the sensors. So we can access each of the sensors that we have, visualizing the information that was recorded from the sensor, and see the historical data, integrated different sensors, so we can get we can compare different data and correlate between different different sensors. This is just, you know, following the same logic to test out or test out our concept for new tools that allow us to interpret information better. I also have a list of sensors out of service, etc. This is also a conceptual idea to manage. The second one is a maintenance registry to get associated to each element within the Revit model, within the BIM model, and within the information of the platform, so we can create maintenance activities associated to users, and also keep a regular centralize all the information for the management of the dam. This is a very simple conceptual idea of what it could be. So filter by activity, etc. We also incorporated a document management system where we have all the archive for the dams. Although all this archive information is also included in the digital twin by type of files, and it can be kept up to date. So we centralize all the management of information. And then we have the predictive dashboard. So we can have a specific dashboard, so we can do the prediction to incorporate the machine learning models. So one of the models that we did not incorporate was the physical one, because we found some difficulties in incorporating the physical model without an API to include it in the platform. Something that we just, well, we didn't give up on it, but we just said it. We saw more value we didn't see the value to incorporate it. And just to finish, this is also a good step because this project was 2 years ago. What we're doing now, and one of the projects that we're doing now, and also in introduction to the next phase of the event, we're actually developing a digital twin for una potabilizadora in the north of Spain, where we're actually developing a platform that puts into reality what we've talked conceptually for the dam. We're incorporating real data, incorporating real management systems to the platform, and yeah, this is something just to show a little bit of what we're doing now. Thank you very much.
Thank you very much, Luis, for this nice presentation. I forgot to say that you multiplied your salary after the master program by 5. Wow. So take the opportunity. Now, I would like to thank all the speakers for this session. I'm surprised that we are perfectly in time. So there is no public questions, but because you have now the opportunity of half an hour to interact, there will be a coffee break right at the end of the corridor. And we hope to see you again at 12 o'clock to continue with the second session that will be on water supply system, drainage, and sewage systems. Okay, thank you, and we thank all the speakers for the excellent presentation.
You think we cannot use this one directly? I think we can use directly this one. No?
Yeah, but do you prefer to use their laptop because Miguel said that the audio everything's
The point is that probably the presentation is a bit heavy. But we
Yeah.
can test the sound also here. If it works, then it's directly from here. Yeah.
because you are more used to
Let's see if Mac is compatible. It should connect already. Or maybe it's this one. Next page. Yeah, maybe. Maybe let me ask the guy. There is a guy there in the technical staff. And the problem is, yeah, the problem is that we have that is very deep, right? And we have a lot of models, right? And it also depends on who we are engaging to depend. Because if the sales or even a solution engineering or a quick engineer, and even most of the time they are not sometimes so in depth, so they can just get the high level views and other readings and not go to the practical aspect. So let's try to put it in a real world cases. But something I like here that I don't see so much in family they really go to the technical
details.
detail,
Yeah.
and they go to
They tap
they
into the
really
black
talk
box.
about the real
Yeah.
the real challenge and the real problems, how to
I don't have this
how
connected.
it can really help them. I don't have this on the Mac.
Do you have it on your?
I can try if I have.
So do you see why But is there? Okay. Okay. I mean, yeah, but it works. I mean, here it works.
Yeah, you should be able to set it down.
Because maybe it's imposed, no? Like,
Wait.
I think we'd be just sure that this video, because it's important that this video, that there is an audio, and we want to be sure that his sound is present.
But if works in your computer, it would work. If it would.
Sorry,
It works in your computer.
this is not my
it will
computer.
work.
Yeah.
This is the
Yeah, the sound will pass.
okay. I think we didn't hear any sound.
First one,
First one
there
sound.
was a little bit of sound.
There is,
It
but-
was-
For me, it's the same, doesn't matter, just it matters that the sound. Para mí, lo único que es importante es que el audio se va a sentir que va a funcionar, porque es más para él.
Zeta?
This is here.
Zeta?
I haven't transferred it. You want to transfer it?
Yeah, the sound was very soft.
Yeah, but the first one was low, was so low that I could understand that it was coming out from these, but it was just the music. It was just the music in the background. So I noticed it was working. So I expect it to be working also. But I'm prepared that the sound will not work and I can speak over the video. Yeah, I have a plan B, but it'd be nicer to have just the voice because it's very professional. It's like a video made exactly by marketing team, specifically very recently. It's very summarized 2-minute video, so it's
You got a permission machine.
yes. Yes, we did it as so specifically.
So you didn't have experience with such.
Yeah, usually I have monthly meetings with them, mount more or less. We have very good relation. I was already with them in person in Toronto. They were already there presenting.
This is
Yes, these and similar projects, because they also use our design solutions for water, not only the digital twin, but the water dams. They are also using everything. So many years. I don't know exactly, but I believe more than 10 years for sure. They are a long user. Yeah, we have a lot of water gems users, a lot over the Europe, over the world. Because in terms of hydraulic model, Bentley is probably the most known
that's what
software
I
for water modeling.
yeah, you know the when you reading it.
So I think they know from. So because it's so well penetrated with the fire,
That's a really good one. No, this is from them. Okay.
Did you copy the?
I just
Okay.
can you safely.
Yeah, it's here already in the desktop, so we can remove.
Sí, nada, no te preocupes, lo cambiamos en un momento. Sí, es que, vamos, yo lo controlo lo que es la pantalla de dentro, pero las presentaciones las tenéis aquí.
Esta es esa, que es el mismo nombre que antes, pero...
¿Cuál es la otra?
Se llama igual, entonces la reemplazas, es la primera. Reemplaza, ya está. Pero entonces la cargas tú o la cargo yo, da igual.
Se lanza desde aquí. O sea, la vais lanzando y yo ya voy cambiando las escenas con los fondos y tal, pero vamos. Aquí, ahora, bueno, tenéis aquí la carpeta.
Muy bien.
La dejo pues ahí abierta.
Venga, muchas gracias.
Okay, thank you for coming back in time. We are going to start the second session. I will, while all the people they come, I will share a funny story. It was March 2025 in Madrid. It was raining a lot. You were very busy dealing with water. And I was with my daughter in the car. She plays water polo. And we were very close to the river. And there were a lot of warnings, like be careful because the river could, it was like March 8th or something like that, 2025. And I said, okay, you swim very well. If there is a situation, maybe you can save me. And my daughter said, Daddy, 9 years old. And she said, Daddy, I think it's better that I survive than we both die. So he's very smart, he's lovely. But I was very thankful to the Canal de Isabel II because you were dealing with a very complex situation, and we didn't have to try if my daughter will have saved me or not. So that's the point. So okay, now we are going to continue with the water cycle. Now we will talk about the water supply and water drainage and sewage systems. And the first talk is again from Canal de Isabel II, Antonio Lastra, and jefe del área de desarrollo de la innovación. And the talk will be in English. Yeah, in English. And he's going to talk about the water supply system in Madrid. Thank you.
Well, thank you very much for the invitation. I'm really happy to be here. It's a bit weird, but I feel at home in this building. It's weird. It's not working, it seems.
Gather? Oh, but it's
here, but it's not.
No.
No.
It's
perfect. Well, I'm going to talk about a digital twin, but in this case about a drinking network digital twin. You know that we have been talking about this, that Canal carries the management of the whole water cycle, of the whole urban cycle, really. Water urban cycle in Madrid region, not only Madrid city, but in Madrid region. But we are going to talk now only about what happens between the abstraction, between the dams of David and the transport and distribution. I mean, between the customer and the dams. And between them, what happens is that we have really huge infrastructure, really huge. Those are the data. I mean, we have nearly a bit more of 17,000 kilometers, maybe 18,000 kilometers. That is a really long network, and is all of it connected. So when we want to do a digital twin, first we have this problem that we have a huge network, but really this is not the important data, because the important data is the huge number of singularities that we have. For example, almost 400 water tanks. So when we are talking about a digital twin, we have to take into account every one of them. Not only the shape, not only the topology, not only all of this data, but the operational data of all of these tanks. But even more important is that we have all of these valves. You can see there hundreds, 100,500 valves, and more than 2,000 flow meters, a lot of press meters. I mean, to put all together in a digital twin that works, that really works, it's a difficult task because of a different situation. I have to say that when we're talking about the digital twin, well, there are a lot of things that goes into the packet of a digital twin. If we go for a traditional definition that is this, I have to say that we already had a digital twin of the drinking water, because in the last 20, 30 years, I think 30, we have a complex model of the whole network. So that's it, a digital twin. It's true that it's a normal hydraulic model that is based in this kind of data. I mean, a lot of links, a lot of nodes, a lot of profiles, a lot of demand nodes. So this is a digital twin that is not in real time, but it's a digital twin. The digital twin is able to reproduce the network topology. And this is an easy task. It's easy now, not in the past, because it was more difficult. But now we know everything about our topology, about our network, so we can put it all together in the model. It's not a problem. It's a digital twin that works with scenarios. I mean, we run the model with minimum flow, maximum flow, the day in the year in which we have more customers, less customer, I mean, scenarios, and it works. And we take into account all of these valves, because you know that a valve seems to be a simple device, but if you close a valve, you lose a pipe. So it's more than a normal device. And then with that, we have set a good digital twin that we use for planning. There are here some colleagues that are working in planning. So when we have a new development in a municipality, in a city, we can put all together the new development and we see what is going to happen and we can analyze if we have to do something new, we have to build something, whatever. We use also for projects because of course when we want to send water to some new development, we can make the proof with different kinds of solution. One pipe, two pipes, one tank, two tanks, pump station, whatever. So we use mostly for planning and projects and for training because, well, people can understand how it works, the network. It's a huge network, so it's difficult, it's not easy to understand the behavior of the water. We have several sources, we have all of this. But the bad news is that with this usual digital twin, what we have is a not calibrated model. It's verified, but it's not calibrated. Because to calibrate a model, we need to compare the results of the model with the real data. But we are working with scenarios, and the scenarios that never happen really in the reality are an invent. So we can verify that the model is working, but we cannot calibrate the model. Also, it's not designed for real-time operation. I mean, for projecting, for planning, it's okay, but if we want to know what is happening right now and why, we don't know, because we are doing a model in not real-time scenarios. And we also assume that the network is perfect. We don't have a problem. We don't have a break. We don't have any anomaly. So this is a digital twin, but it's not enough. What we really wanted is a real-time digital twin that is a step forward and not a little one. It's a really big step forward. We want the network to update more or less automatically. It's not really automatic, but more or less automatically. I mean that when we put something new, we have a new pipe, a new tank, more or less automatically we have it in the model. We want to know what is the real-time valve states. I mean, it's really important to know if the valves are open or are closed or are in the middle. If we don't have that information, we don't have anything. We are talking about real-time. It seems to be easy, but you are going to see that it's the more difficult task or one of the more difficult tasks to see that. We will need, of course, real-time sensor data because what the model does is not works for hypothetical scenarios, but with real data. It takes into account all of the data that we have, put in the model, and then analyze what is happening. And then we can have a calibrated model because we can compare right now what is happening and right now what is the results of the model, compare it, and now if it is accurate enough or not. And then we can do these kind of things that are the thing that we like the most, that is a what if scenario, real time. I mean, what happens if I have a break here? Or if I already have a break in a pipe, what do I have to do around? And I have to what are going to be the customers that are going to be affected? Some of them because they don't have water, this is easy, but another ones because they are going to have less pressure or less flow because we haven't cut them the water, but well, we have cut there, and then the customer there have problems. So this is the thing that we are working on. And it seems easy, but it's not, because a few things I'm going to tell you. First, which are the users of this kind of real-time digital twin? Because we have to focus on this. This is one of the important things. This is not a tool to do it, to show it. That is a great thing to show it, but it's more important to be useful. So the first customer, the first user is the control center people. I mean, the people that are 24 hours, 7 days in a week, in a room in Majadahonda, and David has said it. And then when something happens, they have to know what is happening and how to fix it or how to communicate that we have a problem. So they are the main users. Also the operational areas. Also, of course, people offline, the usual people that are actually using the old digital twin, like planning, commercial, project works. Well, they have a more useful tool now with a real time. And another areas, another part of the business of our company that are involved. But the two first are the first users. And then the problems came, because this is an ideal picture that, well, we go one by one, it seems to be easy, but it's not. For example, people. If we want to have the network topology real time, we need our people to communicate us that they have changed a pipe, or even more important, that they have moved a valve, that they have closed or they have opened. It seems to be easy, but the old methodology for this kind of guys, that I have to say are people that are doing a great job in difficult circumstances. Sometimes it's raining, they are in the middle of a traffic jam, fixing some pipe, they are in the middle of the mountains. I mean, there is hot outside, even here, but outside is even more. And the old methodology was to put it, the annotation in a block, and then when they went back to the office, at the end of the day, they give it to another guy that the day after or 2 days after put it in the system. It works perfectly for a digital twin, but not for a real-time digital twin. So we need them to communicate all of the annotation in real time. The technology is there. They can do it with the mobile, they can do it with the tablet, it's okay, but they have to do it in a rainy day, in the middle of a nightmare, in the middle of a flooding place, because we have a break. They have to communicate this to the system. So this is one of the, I don't want to say problem, but issues that we have. Another thing that we have to take into account, that even, of course, these kind of tools are really, really incredible, big, a lot of things involved. We are going to talk a bit about some of them. But the people that are the principal user are people that are here 24 hours, 7 days a week. And in the middle of the night, 3 in the morning, suddenly they have an alarm and they have to do something. And they are looking not only about the drinking network, they are looking also about the sewer, they are looking also about the dams, they are looking about the pump station, they are looking about the customers that call to the call center saying that the water smells or something like that. So they have really, really a lot of work. So they are not, they cannot carry a model in that moment, 3 in the morning. It's impossible. They don't have the ability because they don't have to do half of the ability. So we have to, even when we have this model in real time in the background, we need a simplified interface to communicate with them, and then they can use it easily, or more or less easily, to do the things that they have to do, to do the what if, to understand what is happening. So this is well, a huge problem, or I mean, even more important than to have a real-time model is to be able to simplify enough to allow these people to use it. And another big problem is the real-time sensor data. We have a lot. We have a lot of data, but all of this kind of device, you can understand that 2,000 devices are not going to work every day and every work perfectly. We have, for example, gaps because we don't have communication, or something is going wrong, or we can have a really good curve at some points that are not, don't have a good behavior. In this case, we are using artificial intelligence to fill the gaps, to clean the time series. And what is more important, and it's a thing in which we are working right now, is in the last one. Imagine that I take all of the data, real-time data that I have, I put in the real-time model, and suddenly I have an alarm in which the model says to me, I cannot put this pressure data in the model because it doesn't work. It doesn't make sense, this data of the pressure. It can be because 2 reasons. One, well, the device is not working well. So, well, I make an annotation and the day after, 2 days after, someone is going to fix it. It's not a problem, but maybe it's a good data, but we have a break. We have a hole in a pipe. Of course, we have less pressure. So it's not the same because I cannot wait until the day after to fix it. We have to send people 3 in the morning to fix it. Well, we can see all of the devices that are around to see what is happening, but it's not easy because we can have another devices that are doing bad because they are also having some problems. So it's not an easy task. So to make this work that allows us to detect if it is a malfunction of a device or if it is because we have a break or something like that. We are trying to fit the artificial intelligence to understand this. Now we are doing things without artificial intelligence, and it's more or less working, but we want to go further. So this last point is not accomplished. We are working on it, but for us, this is really important. Because once again, if I'm 3 in the morning in Majadahonda in the control center, I want to know if I have to run and send the people there, or if I can rest and wait until the day after to fix something. And with all of the devices that we have, well, this can be a problem. I have to say in that moment that we have 2,000 flow meters, but we are talking only about the big flow meters, because now Canal is installing in the customers' houses. You know, some of you, I'm sure that you have smart flow meters, little smart flow meters in the house of the customer that send us also data. We are not using still this data because it's massive and it's really difficult to put it in the model. We are using the big flow meters, but in the future, we will have to put all of this data in the model. That is going to be more difficult to do that. So at the end of the day, we have another kind of digital twin, a real-time digital twin. I have to say that we are in the path to have it. We have part of it, part of the network. We have a lot of things accomplished, but we have not ended yet, because all of the things that I have to do, we have to convince people to make the annotation digitally. We have to be sure that the topology updates are working great. Well, we have a lot of things still. We have to simplify all of our big model to allow the people to use it in real time. So we are not in the middle, but I have to say 70% of the And then it's important to say again a thing. We have the technology to do this. It's not a problem anymore. Of course, can be faster. Okay, but it's faster enough. And we can analyze a lot of data. We can even analyze more in the future, maybe. But now we have the technology, and the technology is improving every day, and it's not a problem anymore. I remember 20 years ago that the main problem was that we didn't have computer to do this thing. We didn't have software to do this. We didn't have communication fast enough to. But now the technology is almost there. But the thing that we never talk about when we are talking about a digital solution is, again, people. For the good and for the bad. Everybody also is people. So to have a really good real-time digital twin, we need the people to be involved. And for me, it's the main thing here, because the other things are about engineering, making calculation, using software. We can do it. But the other thing is a thing that we have to work a lot. This is not, to finish, it is not the only digital twin that we have in the drinking water network. I'm going to show you only 3 fast examples of another digital twin that we have. We are talking about dams. We have, of course, the digital twin that David has talked before. But we are working in this kind of thing. It's a quasi real time. It's not a real time because we don't need, in this case, a real time digital twin that makes the modeling of the 3D modeling of the water system. That picture is from Matazar because it's nice, but this is Santillana, that is near La Pedriza. It's a little reservoir that it seems to be great. The water is nice, but we have problems. For example, we have a lot of birds, and I have to say that the birds shit in the water, and they even die in the water. And depending on the temperature and on the level of the reservoir, we can have problems. And with this kind of system, we are developing an alert system based on water quality. I mean, in the background is a hydrodynamic model, and over the hydrodynamic model, we have a biological and a chemical model that allows now to predict what is going to happen next weeks. And this allows us to do things. We don't have a lot of things to do, but we have, but the people in the drinking water treatment plant can do things and can prepare for something that is going to happen in 2 weeks. Another digital twin that we have in the drinking water system is this that is based in 3D modeling, Navier-Stokes modeling, in which we represent this a decanter, a normal decanter, but we can, with this kind of model, first analyze what is happening inside, because in this kind of infrastructure, we know what are going in and what is going on out. But with this kind of digital twin, we can understand what is happening there, what is the behavior of the water, and we can project new works, or we can modify the operation. We can do a lot of things with this kind of things. And the last one that I'm going to show you is this about the drinking water tanks, because it seems that the drinking water tanks are a normal installation. I mean, I put the water and I get rid of the water when a customer wants it, but inside happens a lot of things if we think about chlorine or another kind of things that we send to the water, because the circulation, you can see it there in these two tanks, is not homogeneous. I mean, we have high velocity, red, we have really, really low velocity, like the blue, dark blue, that is zero velocity. So when we put chlorine in one point, the mix is not really good. So to understand what is happening, and what is more important, to project new works to improve the behavior of the water inside and of the mix of the chlorine with the water, we use this kind of digital twin that is based in Navier-Stokes model. And just the conclusion for me, always when I talk about digital twins, and I like a lot this kind of models, I like a lot the digital twins, but for me, the important thing is this, that to have a really good digital twin, of course, if it is a real-time digital twin, it's more important. We need all of the people of our organization like us to be involved. And when I'm talking about areas, I'm talking about people. I mean, from the CEO, maybe from a director, to the worker, a normal worker that is in the field. They have to understand the importance of all of this. And this is not their problem, it's our problem to teach them and to allow them to become part of our work, because if not, we are not going to have a real-time data. Thank you.
Thank you very much, Antonio, for this super nice presentation, realistic, and emphasizing this idea of the importance of engaging the teams in the realization of digital twins. So a nice overview. I have a question, it's a curiosity. You know that it is always said that there is an strong relationship when there is a soccer game between the water consumption and what is going on. And now you have AI models that can predict the future. So will Spain win the World Cup, or it's hard to say, because yesterday we have an anomaly. Okay. Okay, jokes apart, I think that during the discussion we will have time to interact. So thank you again. Now, many people are asking why this is in English. This joint master, by the way, you can enroll in the master if you want. And this initiative is supported by 5 European universities, and there are people watching these presentations online. And to give an European dimension, it's my pleasure to also to have a presentation of another water supply system, in this case of the city of Rotterdam in the Netherlands. And the presentation will be given by Simone Botari and Miguel Suarez from Bentley Systems. Thank you.
No sé cómo ponerla, a botarla así.
¿Pero cuál? Está marcado.
No problema, para mí no es un problema. Buenos días a todos. Antes de empezar, me gustaría disculparme porque la presentación está en inglés. Somos en España, puedo hablar español, pero creo que seré más claro y efectivo si presento en inglés. Muchas gracias por su comprensión. So let me briefly introduce myself. I'm Simone Votteri. I work in the strategy team of Bentley Systems. I bring in around 10 years of experience across corporate finance and corporate strategy. And water is one of our, like, say, main areas of focus. And it's both like where we are investing in terms of long-term and as well like one of the key application in terms of engineering. Today, we will bring to you a real case study, so operational digital twin for Rotterdam water systems. And we want to show you how we moved, we helped Rotterdam in moving from traditional planning to real-time and data-driven approaches. Before moving in, let me show you the agenda. We will just give a brief introduction about Bentley. Then we will move about some key facts about water challenges. Some of the topics we already discussed that have been already presented. And then Miguel, my colleague, will present you the digital twin application for water and the case study. Let's talk about Bentley Systems. Bentley System is the infrastructure engineering software company. Our vision is advancing the world infrastructure for a better quality of life. We work across 5 industries: cities, energy, transportation, mining, and of course, water. And we cover the full infrastructure life cycle. So from design to build, operate, and finally maintain. In terms of key figures, like we are present worldwide, we have over 42,000 accounts, and we operate across more than 70 countries, and we employ over 6,000 employees across the world. I have strong workforce and presence in North America, Europe, and APAC. And our software are like, let's say, cover different parts of the infrastructure sectors. Some, let's say, flagship brands are MicroStation, ProjectWise, Synchro, and of course, water application like Open Water and so on, including digital twin. Moving now in some key facts. Water scarcity is already a systematic issue affecting around 50% of the global population, not a future risk. So it's something that is already happening today. Around 3.5 billion people lack safety management sanitation. And around every year, at least 1 month of severe water scarcity affects 2/3 of the world population. But the core challenge extends beyond scarcity with widespread inefficiencies, leakage, and other treatment. So consider that some of the operators here they're aware that energy-related costs represent up to 40% of utilities' operational budgets. Utilities on average lose between 25 and 40% of the drinking water in distribution. And what is defined or considered world class, it's a loss or leakage of below 15%. In this scenario, global water demand is projected to increase 60% by 2030. And the global expenditure around infrastructure is 35 billion euro per year between Americas and Europe. Water is also at the same time one of the largest underfunded infrastructure sectors. Public budgets are limited and private capital participations remain still low today. Structural transformation is required across investment models, operational performance, and technology adoption. At the same time, on the other side, digitalization, real-time monitoring, and asset optimization represent the primary levers to close this gap and improve system performance. Demand for infrastructure projected is growing, tighter deadlines, expanded requirements, and limited workforce capacity. What's it happening? Aging infrastructure. Many of the cities' infrastructure have been built 50, 60 years ago, and the municipalities are investing a lot to expand their water network and invest in new projects and delivery. At the same time, there is a big growth in urbanization and population growth,
like thinks about the city of Madrid that is continuing to increase its density, and also it's also expanding new neighborhoods and horizontally. And finally, AI and digital transformation drive opportunities unthinkable a few years ago. Consider like Europe is one of the leaders in this space. The real question is what can be done to spin things up. Europe is adopting a 3 layers, like let's say framework. The first one is regulatory pressure. So water efficiency first is embedded as a guiding principle in public and private investment decisions. There is a strong push on water reuse and circularity, and also there is a tightening in water quality and pollution standard. Regarding technology adoption, digitalization again is positioned as a core leverage across the full water infrastructure and operations. Deployment of digital twins, as we've seen also today, and real-time monitoring reduce leakage and optimize performance. And finally, like another like super important point is the development of shared data platforms and open standards to enable interoperability at scales. Imagine tomorrow you will have one system working on the city of Madrid, one system working on the city of Valencia. But what about if these 2 systems can talk to each other? And finally, system level thinking. So the adoption of a one water approach, integrating like the full life cycle from source to reuse, and the shift like from supply expansion to end-to-end system optimization and resilience. So this was like a very brief introduction about water challenges. I will leave now the space to Michael that will drive you more in the technical approaches and our case study. Thanks.
Thank you. Thank you. So just introduce quickly myself. So I'm working as a product manager for Bentley Systems. I'm coming from Portugal, so quite close. And it's a pleasure here to be presenting about our digital twin offering for water and also talking a bit about our case study with Rotterdam City. So we have been working with them very close in the last years, and we have very close interactions with them, and we have developed or co-developed the software that it's already also being used by other users across the globe. Okay, so first, in the last presentation, we already heard a little bit about what means the digital twin. So just summarizing again, a digital twin is a real replica of the physical system. This should not be just a static replica, but a replica that is live. So it's really, really important that we connect this system, this digital twin, with real-time data from real-time sensors so that we can infer exactly what's happening in real time in the field and bring that information into this replica. So this is a real-time digital twin where we can also model performance, behavior, predict future behavior, and also taking a look and investigate all the past behavior. This digital twin should be comprehensive enough so that we can tackle the different asset life cycles. So the same digital twin could be smoothly used from planning, design, analysis, construction, and operation. We have been doing this specifically, for example, with Evides that I will be talking. They have started using our solution for the planning and the design of the expansions of the system, making adjustments to the pipes, to the network, and then they have moved to the real-time operations, and I will focus today more on the real-time operation side of things. So just in a quick introduction on how a high-level diagram of our digital twin platform. So basically, on the left, you can see the main inputs into this platform. So this is a cloud platform that you access through the internet with the login, username, password, accessible to multiple users. So the idea is that we are going to connect with existing data that the water utility already has, and utilities already have a lot of data, huge amounts of data. They are collecting big amounts of data. Typically, the data is siloed in different departments in different systems. So we have the SCADA data, smart meter data, AMI, data loggers standing in specific database in specific systems, the GIS data in another department, hydraulic models, if they are available, usually sit with the hydraulic model department, work orders, billing systems with the commercial department, other engineering data, and we are also fetching automatically weather data. We have also a service with EBM to bring all this data.
So all the data that already exists in the water utility is connected to, automatically brought to this platform, so that can be easily assessed by anyone. We are treating huge amounts of data, so the idea is not just to display the data, of course, but also to use powerful analytics, statistics, machine learning, AI, to bring and transform that data into useful insights. So on the right, we can see at a glance a quick division of how our solution is divided into several modules. So we have a specific module for real-time monitoring. We have specific modules for pump assessment, tank assessment. We have specific models for event management. So automatic alerts are generated. Users can be notified by email. They can manage those events, and they can even simulate response to those events using the hydraulic model. We heard before also in the presentation before. So using this model to simulate, for example, impacts of pipe breaks, sudden pump shutdowns, big demands that are added to the system, how much this will impact the system, the pressures, how many customers will get impacted. So we can manage and simulate all those impacts. Water balance calculation are automatically done. Water loss is calculated per each zone. We have a module specifically for customer analytics to give insights in which meters or customer meters should be replaced, which ones are losing more revenue because they tend to undermeasure. They can be oversized, undersized, and utilities usually or typically are losing significantly amounts of money due to inadequate customer meters or because they are aged, undersized, or oversized. The real-time model. So this is not a static model of the system. This is a real-time model of the system. Their hydraulic model is embedded into the digital twin platform, and we automatically connect that model with the real-time sensors. Flow, pressure, level, pump status, all the real-time sensors from the field are adjusted into the model automatically. So the model is running with the real flows, is running with the real status of the pumps measured from the devices, with the real, for example, the real setting points for the pressure reduction valves. So we assure that we have a real-time model. Also, we have connection with the valve status through an API. So all the valve status updates are there also in real time, smart meters. Everything is automatically updated into the model. I will just pass a quick 2 minutes video of the solution, and then I will show you the Evides use case. So let me just, so that you have a quick understanding of how the solution works. It summarizes all what I've spoke about. Okay, so maybe you don't hear the sound, but I will be speaking a little bit over this. I will be speaking over the slide. So these are some examples of dashboards that we have in our solution. This is the real-time view of the system with the real model there that is running in real time, fed with the real measurements from the sensors. And then you can check every variable, pressure, flows, even water quality, chlorine concentration, water age. You can simulate impacts of events like these pump shutdowns. And if there is a power outage suddenly, how many customers will be impacted? Do I have enough storage at the tank? Water balances are automatically calculated for each zone. This is all automatic according to the diagram of AWA, EWA also. You can check the evolution of the different components along time. So the revenue, the billings, and you can compare also the different water balance components per each zone. So understanding which zones we are losing more water, water losses or real losses or apparent losses. So we have a powerful alert event detection system that will detect anomalies whenever flows or pressures go out of expected trends. The expected trends are those gray bands that you see here. Real-time data is the line with the dots. And we can even help geolocate the problems inside the zone. These red nodes, it's the most likely location of the issue. We have several dashboards, pump dashboards where you can check the pump operating points, flow, and head. You can check pumps efficiency. You can check in real time the tank levels. Here, another view for the tank levels where you have real-time data with the expected trends or the patterns at grade. And finally, you can also use this for capital planning for identify the pipes at more risk. So you can use a likelihood of failure analysis, consequence of failure analysis, and then calculate the final risk based on the likelihood and consequence. And from there, identify the pipes that might be at higher risk. We have a section specifically for all the administration section. Users can manage all the administration parts. And they can build their own reports, their own pages in WaterSight through Power BI. So these are customizable dashboards that they can add, like this one. It's just an example of the Power BI reports we have. This was fast, but I will show you now. I will speak now a little bit about Evides use case. So we have users around the globe, also in Europe, in other continents, in North America, and South America, Asia, and specifically around implementing these digital twins at scale. I can just summarize three key utilities. For example, Evides that I will be talking, it's in the Netherlands. They are supplying about 2 million customers. They have about 1,500 live sensors, 600 smart meters. We also have this digital twin implemented in real time for Washington City in the US. Also in Brazil, the two largest water utilities, Sabesp, Aegea, so they manage the São Paulo city and also Rio de Janeiro. We have in other cities in India, also in here in Europe, for example, in Warsaw for the full city. So the same platform that can be used for different users and can be adapted to different maturity levels. So specifically for Evides, so I already mentioned they supply 2.5 million customers. From their water, about 90% comes from river, 10% from groundwater, and they manage about 12,000 kilometers of main pipes. So it's a very, very huge network. They are also one of the biggest utilities in the Netherlands. So the solution is quite comprehensive, and today I will be focusing mostly on the event management workflow that they are using actively, almost, I would say, even every day. So how does this work? So basically the event management, they get an alert, an event that they need to manage, and how they usually use the solution to tackle that event. So first, in terms of input data, we are connected in real time to all their flow and pressure sensors, also smart meters, also other level sensors. All this is feeding into the model and updating the model in real time. So we also have the model there. We are also inputting information from the GIS, for example, the zone's boundaries. It's important for the leakage geolocation that I will be speaking just in a bit, that we have ideally flow and pressure for each DMA. So they have some pressure DMAs, sometimes one sensor, sometimes 2, 3 sensors in each DMA. The first part of this is the alerting system. So WaterSight, our digital twin solution, it's called WaterSight, will automatically generate an alert whenever there are some deviation to typical trends. And you can see here in the picture below, we saw similar graphs for the dams, and it's the same logic here, not a displacement, but here it's a flow increase, can be a pressure decrease. So the real-time data is the red data, the red dots. They are outside the bands that are the patterns that are below. That should be what we should be having in that day for that system. And this is calculated in real time using also AI, machine learning statistics, taking into consideration also external variables like temperature, precipitation. Here it's a real event. So the flow go out outside the traditional typical flow for at least 3 days there. It generated an event. We have other events being generated. Sometimes it's just smaller deviation. Sometimes it's bigger deviation, depending on the size of the leak. So an email gets also generated to the user. They get notified by email. After that, in case they have the model there updated and calibrated. And because the model is already running in real time in the digital twin, being fed with flow data, pressure data, smart meter data, valve status APIs, that is already a very good model of the system. They can then trigger the geolocation run. So how does this work? They have an event that is generated. They have to validate the event, so they discard if there is any other potential reason for that event. For example, some large customer consumption during that time, so they can easily compare their large customers that are there in the platform and see if that is due to large customer consumptions or other planned events that they have in the system. Someone was there and is doing some planned maintenance activity. So after they discard that it's not that it's something real that might be a leak or a burst, they then trigger the run geolocation. The trigger run geolocation is just a click of a button, run geolocation. We want to make sure that they first validate the event. They click on one button, single button, and then automatically in the background, our platform will start to run several scenarios automatically without expose this to the user, but we'll be running multiple model simulations for each node, simulating a leak in each node automatically. So we run in parallel hundreds of simulations, simulating a leak in each node. At the end, we will have results for each simulation, all in the background. The user does not see this. At the end, we will have results for each simulation where we will be able to compare modeled results at the flow and sensor boundary conditions and the measured results. And for those simulations where we have the best fit between modeled and measured results, that's where we have more likelihood to have a leak. So at the end, the results that will be exposed to the user is like this map color-coded in the nodes, where the nodes with red are more likely to have a leak, the nodes with blue less likely to have a leak. After this, what they do, they already send the crew specifically to that area. Depending on the amount of sensors, it can be 20, 30% of the DMA, or it can be even to the street level. But it already helps them a lot. Instead of investigating through all the zone, they can already send the crew to that specific site. And just to mention that we are talking about Evides, they have a lot of crop fields. They have a lot of water bodies. So even sometimes medium or big leaks are difficult to detect visually because you have the field crops that don't allow you to see that, or you have the water infiltrating into the channels, or sometimes you have significant leaks that are running underground, invisible. So this is helpful for them. After they find the leak, then they can use also the platform to simulate beforehand or when they are in the field to understand what are the best valves to close in order to mitigate the impacts on the customers that are affected. If we close these valves, how many customers will get impacted? And maybe we can advise or warn those customers, trying to understand best mitigation measures. All that can be simulated also using the model. So I will show you some examples with Evides now. The first video is about geolocation of leaks. When we started with them, and when we implemented these, they started to do some blind hydrant tests. We didn't know anything about it. They just start to open hydrant tests randomly to check the accuracy of the leakage geolocation algorithm. So this was to test or to simulate a real leak. This was done in the beginning, and the results were very, very good. And they are now using this for real-time detection of leaks. So here is an example. They open an hydrant. It's quite a significant amount of flow into the system. First, this gets an event in water site. You see that small spike there with the red dots. It's a spike. It's an event that is automatically generated. We can understand the volume lost. Then they run the leakage geolocation, and it starts to calculate automatically based on the model runs where is the most likely area. And you will see that as this is calculating, it's showing the progress in the results, so they can already have immediate access to the results. They don't need to wait too much time. And it will start to get more granular, and these orange areas where it's more likely, and then it will start to be even more granular, and putting here also some red nodes. So this was an example that they did a blind test. We didn't know anything about that. They just tested by themselves. It's exactly almost catching in the exact spot. And now so the exact location is there on the red, so it was just perfect. This is just an example, but they are using this already for real leak detection for almost 7 months. We have regular meetings with them every month, and they are talking honestly about an efficiency of 70%, 70 to 80%. So this means that from all the events generated in water site that they run the geolocation, in 70%, it can really guess and narrow down the right area for them of the leakage. Sometimes it's a bigger area, sometimes it's a smaller area, but in 70% of the cases, it's giving them the right indications.
Something also curious, they already have a workflow where they run, so once they receive an event, they run geolocation if they suspect it's a leak. And most of the time, they are also already sending a drone before sending a crew team to check for in that location if there is something there. So also optimizing their crew drive and so on. Other examples. So it's not only about geolocating leaks, but it's also about understanding impact of the leaks. So with the platform, they can also understand, okay, if we have a leak of 10 or 20 cubic meters per hour or 50, whichever flow they want to simulate, I can understand easily the impacts in my system. So on the left, for example, is the real-time scenario for that day without any leak. So the pressures are green. Here we are talking about probably 40 meters, 30, 40 meters. So they have a lot of pumps and pressurized systems network through all their pumps. On the right, they simulated a leak, a big leak, and they could check that if they had a big leak in the system, all those customers, you see the yellow dots, they have some numbers there. It's the number of customers that are impacted, and all that pink color is because the pressure got dropped below 15 meters, more or less, water column. So they can easily simulate the impacts of events. If we have a leak in the system, how many customers, how will be the pressure, how many customers will be impacted, how many customers will be without water. These orange dots that we have here, it's because we have low pressure customers, but if there were customers without water at all, it would start to be red dots, red circles. And another example with the fire they had in the system, I will play the video and I'll be explaining. So they had a big fire. The firefighters needed to take water from the system to fight for the fire. It was a big flow taken from the system. So a bit of stress into the system. This event was clearly catched by WaterSight, by the platform. You can see this big increase in the flows. This was the fire event. It completely got out. You can check the volume lost. Maybe here we don't see very well, but this is important for them to measure and register the unbilled as authorized consumption. Then they can run the event like a fire event in the system and specify the location of the fire and understand, okay, if we have this fire and we have this water coming out of our network, do we have problems in terms of pressure with our customers around? So they simulate that with the real fire flow, with the real flow, because the real flow we also calculate from the application to the event. And it's a big one. So we are talking about, they are putting here, I think it's 215 cubic meters per hour. So it's very large flow during 10 hours. They are running this event, and then they can, after that, they can check the pressures with this additional demand in the system. How will be the pressures be in the system? Maybe you don't, let's just calculating, it's just calculating, yeah. So the nodes maybe you don't see, but they are green, so the pressure is not so bad, it's still good, but there is a decrease in pressure from about 40 meters to 30 meters. So although you have a big decrease in pressure from 40 meters to 30 meters, it's still much above the minimum pressure, so you don't get any warning or any customer highlighted because you don't have low pressure customers, because the decrease in pressure is not sufficient to cause problems in the customers. So this is an example. Another example with a real burst caused by a contractor. So they have some expansion works in a rural area. And some constructor by accident created a burst, a break in the system. They needed to identify they wanted to do the repair, and they found the best valves to close or the nearest valves to close. And in that scenario, those are the red valves there. In that scenario, if they close those valves, all these customers would get impacted during the intervention. So we are talking about, you don't see here, but it's like 1,000, almost 2,000 customers are impacted with this closure. It's a rural area, there are not so many valves. But then, and you can see the impact also on the flows and the pressures. But then they started to use also digital twin to study other alternatives. Like, okay, instead of just just blindly close some valves here, let me see if I can close some valves and open other valves
to do some bypass of water and mitigate the impacts on customers. So they use this also to simulate, and they started to open other valves that usually are closed, boundary valves from DMAs. Usually they are closed for operations. They open them temporarily to create water passing through another direction. They closed other valves. They were able to isolate still the area for the intervention, and only 200 customers were impacted instead of 2,000, right? So this is also an example where when applied digital twins, they can also mitigate the number of customers that might be impacted due to these events. So they have a real live digital twin in the system, and they are real using in the real-time operations, not only for leakage, but also response to these events like fires and others. And that's it. Thank you.
Thank you very much, Miguel and Simone, for bringing these examples and the capabilities of these tools to approach the digital twins for water infrastructures and water supply system. So now, again, Canal de Isabel II, we go down to the river, and we started with the reservoir, then the water supply system, and now is the turn for the drainage system in Madrid. So it's my pleasure to introduce you to Jaime Flores, right? Yeah. Deputy Director of Research at Canal de Isabel II. The floor is yours. Thank you.
Thank you, Ignacio, for your kind presentation. Good morning, everyone. Thank you, the organizers, and thank you all for your attention. Let's talk about DrainCam, a digital twin for the Madrid's urban drainage system. First of all, as it is a requirement for every European funded project, let me do the dissemination requirements. And let's say that this is a project that has been presented in the first call of the PERTE, these strategic projects for recovery and ecological transition. In the second call, exactly, this is a project of around 26 million investment and 10 million funding. Then, of course, you all know Canal de Isabel II, because my previous colleagues has presented some figures, and you all know that we are managing the whole water cycle. But you probably don't know that we are also energy producers. In fact, we are the largest energy producer in Madrid region. Anyway, these are some main figures about our reservoirs, about our drinking water treatment plants, distribution network. My colleague Antonio has talked about that, and our digital twin. But let me highlight some figures about the drainage. And in this sense, we have 73 storm tanks, 155 wastewater treatment plants, and more than 16,000 kilometers of sewer network. So it means that it seems to be complex. Do we need DrainCam? The answer, of course, is yes. This is a quite complex system. To optimize the management of all these infrastructures, we need some help. And there is just an example. This is the last part of the Manzanares system, when you can see wastewater treatment plants, tanks, valves, level sensors, flow sensors, pluviometers, all these infrastructures together, and all this information has to be in the same platform to be used for the operators as a decision-making tool. And there is also an aspect that has to be taken into account, not only quantity, but it is even more importantly, a quality criteria. This system is also focused not only in the management of the quantity of water, but also the quality. And it weighs more. Quality is much more important. These are the main objectives of this system. Of course, to protect water bodies, improving the state of our rivers in the Madrid region. It's also focused on the spillways. These points of these charts when it is raining a lot and our system is not able to reduce contaminants and return to the river water in the exact terms of quality. Floods, improving the floods discharge and management of in urban agglomerations. Forecast, we are going to see that this system has a platform where these gather, we collect all weather information and climate information that is used. Of course, this system also used for reduce energy. The optimization will help us to reduce energy consumption. It is a decision-making tool for our operators. And we are focused on including in these systems all technologies that can be applied. We have seen some with the speech of Antonio, and we are going to deep on these technologies, artificial intelligence, modeling. Let's see. I'm going to describe this system. What is DreamCam? This is made up of 3 modules. The first one is a climate model. When we collect information from our pluviometers, our rain gauges, the information from AEMET, you know, the Spanish agency for weather forecast. CIMENA, also another platform for weather variables, and our radars. Let's say that Canal has 3 radars in the C-band, sorry, in the X-band installed in the Madrid region. And we are now trying to relocate one of them because it is not well located. It's affected by a close energy station, and the lightning affects the behavior of this radar. And we have recently purchased another one in the C-band, a big one. And we also are using the radars for the AEMET. So it means that we collect information of every source available, and this is very important to know the intensity of the rain forecasted. Another module is for the network information, the sewer network information. We have a GIS for those 16,000 kilometers of pipes, a very accurate GIS. And we are expecting our sewer network, let's say that it is completely inspected every 4 years or almost 4 years. We are using the usual technologies, TV cameras, operators, but recently we have designed and manufactured a specific device. It is a self-guided drone to avoid the people to enter this, let's say, harsh environment. And it is self-guided. And this is the technology we are recently using for this inspection. This drone is equipped with a LiDAR sensor, and it is registering a 3D modeling of the interior surface of the collectors and pipes. And also, this information is also used in a quick processing process to self-guide it. The drone is able to avoid obstacles during his flight. And of course, all this information register now is recently processed using AI. It allows to be quicker. A lot of information that can be processed with AI. It's quicker, but also it's more adjective. We are avoiding the experience and the skills of operators when we are using the recognition of some patterns for defects, breaks, and problems that we can have on our collectors using AI process. The third module is a sensorization. We have a lot of sensors for flow, quality. They are installing collectors, outfalls, wastewater treatment plants, our tanks, and all discharging points. And these sensors has to be robust, of course, because the environment when they are installed is not the best one. And we have turbidity, we have conductivity, we have level sensors, we have automatic samples, and so on. With all these modules and our models, we have been talking about some of our models, real-time urban drainage models and urban drainage models in the scenarios as in the area of water supply and distribution Antonio has mentioned. With all these models, we have seen some of them, I mean these Acelator settlement tank or a spillway or the Santillana reservoir or this toroidal tank. These models help us to use this system. So models, data, this is a decision-making support that helps the operators for an optimum management of the sewer network. The complete system has also a visualizer. You can set some alarms and threshold, and in future, because it is not the scope of the funding project, but it is going to be really achieved by Canal de Isabel II in future, we will have a future remote control of all these infrastructures. Just to show you how it works, this is the first screen of this visualizer. We will have the Tagus River Basin where Madrid region is set, and we have a kind of dynamic zoom. If you zoom in the Madrid region, you can have the river basins that we are managing. For example, in this case is the managing of the river basin of Manzanares. And in every screen, you will have some data. For example, number of discharging that have happened, volume that has been discharged, the contaminants, and every variable can be also be shown in different periods of time, a week, a month, a year. Again, zooming in this river basin, we can have the subsystem of the basin. In this case, is the endrinal system with the same variables or others, and we can also zoom in to every infrastructures involved in this system. For example, we will have a storm tank with 2 deposits, or this is the case of a wastewater pump station. Thank you very much.
Okay, thanks to you, Jaime, for this next presentation. You will have the opportunity in the roundtable also to share your ideas, but I think that you show a very nice case at the last part of the life cycle of the water. So in these events, we usually mix academia, industry, and administration, and now is the turn for academia. Usually we have a reputed researcher from another institution, not from UPM. And in this case, we have chosen CIMNE, which is a highly reputed research institute in Spain. And we are lucky because we have an excellent researcher. He is the director of CIMNE Madrid. He's alumni of this school, PhD from Universidad Politécnica Catalunya, and now is full research professor. And he will give an overview. We go back to dams, and he will give a comprehensive overview of the use of artificial intelligence in dams engineering. So Fernando, my pleasure, and the floor is yours.
Okay, thank you, Ignacio, for the invitation, for the very nice presentation. And it's a pleasure to be part of this event, but now also to come back to this building where I spent so many hours as a student, mostly, then as a professor as well. I'm going to talk about digital twins, of course. This is the topic of the event, focused on dams, and in particular, the relation with artificial intelligence. So this is the outline of my presentation. Of course, you are now experts on digital twins, so I will skip part of the generalities, but I will provide my personal point of view on that. And then I will focus on LLMs, large language models, tools that we are probably using every day, and how can we better use them and in this context of digital twins. I will talk about how they are built, trained, and what are the limitations, etc. So then I will show some examples of application and some conclusions. So what is a digital twin? Of course, a lot has been said today about that. This is probably, as far as I know, the first time that that term was mentioned in 2012 by the NASA. And they spoke about ultra high fidelity simulations, important thing, of course, integrated with additional information with the goal of mirroring the behavior of a physical system, right? So, well, there are other more general definitions. A lot has been said today, but it's a very concise and accurate term, I would say, because it's a digital representation of a real world entity. Everybody can understand that. So when I was thinking about this talk and reviewing this concept, this slide came to my mind. I have used this slide quite often over the years. It was like the core of my PhD back 10 years ago. These ideas were from Professor Lombardi from 2004, a very well-known dam engineer. He didn't use the term digital twin, but the ideas, in my opinion, are quite aligned. He speaks about the actual dam, actual response, and on the other hand, we have the idealized dam, some model that predicts the behavior of the dam. So he said that the comparison between the predictions of the model and the actual response of the dam is the key element for decision-making in dam safety. So he didn't know the term, but I guess these ideas are more or less what digital twin, what we understand these days for digital twin, right? So in dam safety, we have sensors on the dam, we have models that predict the response, we have our engineering knowledge to interpret, to analyze these models and the results. And of course, we make decisions for short-term operation or for predictive maintenance on the long term. So we can say that in a way, dam engineers were doing digital twins without knowing, in a way. So, and in turn, this reminded me of this cartoon. It's quite popular in machine learning. You have a crack on the wall. It's called statistics. No one takes care. But if you put the frame, you call it machine learning a little bit better, and you call it artificial intelligence, and everybody comes and pays attention to that. Well, I thought that we could somehow do some analogy with that. We engineers have been working inside. We are a crack on the wall. We call it a numerical model a little bit better, but we find the right term, we get the attention. In fact, I work for the International Center for Numerical Methods in Engineering, and maybe we are 40 years old, and maybe if we were to be found now, maybe our name would even be the Center for Digital Twins. Well, what I mean is that, well, the terms are important, but this is quite related to things that we have been doing for many years. So what tools have we dam engineers have used in the past to simulate, to replicate these huge, big structures? Well, I would say that I would want to start with these models. This is Giovanni Lombardi, by the way, back in the 60s, last century, structural model. This is not a digital twin in the sense that it's not connected to the real-time structure, but it is a replica still, It's a replica in the laboratory in this case. So we can say that this is like an analog twin, I don't know if the word is even invented, but we can call it an analog twin. These models are no longer used, but they are indeed used for hydraulic structures. And I don't know, these photos are from the CIDIX, but I guess that here in this laboratory, maybe you can find some of these models. They are still in use, very useful. And again, an analog twin, But we also, dam engineers, have digital tools. And of course, the finite element method is something that we often use, from the early models by Sienkiewicz to more sophisticated models. Some of them have been shown here before. And also the database models. Again, we started with something on the left, simple analytical approaches, and these technologies have evolved, incorporating machine learning, neural networks, simple, then more sophisticated architectures with, in principle, higher accuracy and higher flexibility. And now we have totally new tools in the last 2 years, more or less. I used to ask the audience who has used one of these tools in the last week, but for sure, everyone has, I bet. This is just some of the options that we have, but they are very powerful. but they also fail sometimes. So I'm going to spend some minutes now talking about how they are built, what's behind the scenes, what happens when we open one of these softwares. We typically find a chat, we enter a query or a question and we receive an answer. So what happens between our text input and the text that we receive as an output? Well, there are a number of steps there that I'm going to very briefly describe. First one is the so-called tokenization. So our sentence is split into words, you can say, what they call tokens, so pieces of text. And each piece of text, each token has an ID number here on the right. By means of a vocabulary or a dictionary, no? Every word has a number, that's it, okay. So each of these numbers in turn have an embedding associated. And this embedding is nothing but a very long vector with thousands of components. Each component is a number, and its number captures a nuance, a detail of the meaning of this word. But we have thousands of components. So our input is converted into a set of very long vectors, numerical vectors. These vectors go through this other module called multi-head attention module. This is nothing but a set of matrices, these key K and V matrices. They are very big, but the mathematics are very simple. Just dot product between vectors and matrices, nothing but that. And the goal of this module is to capture the context. You know that the word, the meaning of a word depends on the word itself, but also on the context of our question. So this is how these models capture the differences in the meaning because of the context. So the result is another set of vectors that are passed through another module. And this is nothing but a neural network that we've been using for years. A set of layers. Mathematical operations are simple, not that difficult. The difference is on the size, the number of parameters, the number of neurons, the number of, as we will see in a minute. So the output of this MLP module is another vector. This vector has the same size as the dictionary. And the components of this vector are the probability of each of the words of being the right answer to our question. But what we get is not always the word with the highest probability. No, instead, these models do a random sampling among all the possible words, conditioned on that probability, but still random, okay? And why do we need this random component? Well, of course, we are engineers, we're on the left, no? We want 2 + 2 = 4. But if we were comedians and we want the model to tell us a joke, we don't want them to give us the same joke every time, right? So the randomness is important as useful in many contexts. This can be controlled with this parameter, it's called temperature. So we want low temperatures for robust, solid responses, but in other environments, we may want to read this temperature high, okay? But there is some random component here that we must keep in mind. We must keep in mind. So how do these models look like? This is a very nice website. It's interactive. Here, just took some screenshots. This is how a GPT of this kind looks like. If we zoom in, we can see the embedding vectors at the beginning. We can see these attention heads, this set of matrices. Each circle there is a coefficient. The operations are the dot products between the vectors and the matrices. Here we have the MLP, big set of parameters there. The operations are simple. Each couple of attention heads plus multi-layer perceptron form a transformer module. This small model has 3 transformers. And the output there below on the left, very tiny vector is the probability vector that I mentioned before. So this is what there is inside these models. But this is a very small model, even though it has 85,000 parameters. If we compare this with a not so small model, it's that dot over there, I don't know if you can see it, that's our Nano GPT compared to a GPT-2. But this GPT-2 is small and old model. The models we're using these days are bigger than, but not so big that this GPT-3, 174 billion parameters. And I don't know, you probably can see the GPT there as a dot. But the structure is the same, set of matrices, transformer modules in series in parallel, and the output, I don't know if you can see it, but here is a vector with the probabilities, okay? So all those operations converge into that small vector compared to this size, okay? So of course, this is okay, but how can we get to know what is the right value of each of these billions of parameters that give us the useful answers? Well, this is done with a training process that follows basically these 3 steps, similar to the steps we follow when we want to learn something new. We read books, then we look at solve problems, and then we try to solve new problems without knowing the answer. We get the evaluation from the professor, and we learn even more. No, this is similar to what's followed for these models. First, a lot of text, and then in the second and first steps, a lot of people, experts, are involved. They provide solve problems for the models, and they, in the third step, evaluate answers from the model and provide the feedback so that the model fine-tune their parameters. Okay, this is an expensive, costly process. You can do it at home. If you buy a GPU, 5,000 euros, you just have to wait 665 years to train up one of these models. I was joking, this is not doable. Of course, it is only feasible for big companies, okay? Of course, they use servers of GPUs or CPUs, etc. So what are the limitations? They are very powerful. Most of us have probably made use of the capabilities. Hallucinations, you have for sure experienced this. This is an example on dam engineering. I asked for a reference to justify some question about dam engineering, and the answer was about an ICOL bulletin. ICOL is the National Commission on Large Dams. So I went to the ICOL website, and there is a bulletin with this number of and date, but the title is totally different. So you need to verify. We need to verify, and we need to be able to verify every answer that we get from these models, because even in this simple question, they may fail. Okay. Another limitation is privacy. Sometimes we don't want to share our data, our safety reports, our knowledge to the internet. No, we don't know what's going to happen with our data. One option, obvious, is to run one of these models in a local computer and at the office. These are names of different software solutions that allow us to download one of these models. There are many models out there in Hugging Face for download for free. You can download them, and with this software, you can create this interface that you can run locally. This is an example, a toy example that we ran at the office with this Mistral 7 billion parameters in a computer, and we interacted with it. And well, not the best model, but can be useful because, and in particular, it has the advantage of privacy. Another limitation is the lack of technical knowledge for specific questions. No, it has been trained on lots of data and text, but not so much about dams. No, this can be alleviated with this process called RAG. With RAG, you can create a knowledge base or provide specific documents that are processed, and these documents are then combined with our query to generate an improved or enhanced input to the model, so that this output focuses on the knowledge base that we have provided before. Another limitation is the dependency on the prompts. The prompt is our question, what we put into the chat. We said that this text is converted into vectors that go through mathematical operations. If we modify one word, we modify one of these vectors, so the output is going to be different, okay? These are hints by this researcher, very well known, Andrew Karpathy, who was director at Tesla. Of course, this depends a lot on the kind of tasks that you are want the model to do. This is more for coding, but in our field, I found 2 of them quite particularly interesting. One is before any big task, let's say, stop. Don't start answering. Give me a couple or 3 options, and then I can guide you and say, yeah, this is more promising, this is accurate, and forget about that. Otherwise, you can wait a lot of time until the answer is generated. And the other one is the 4th. If you don't know about something, wait, stop. Don't tell me anything. Tell me, I don't know, or I need more information, or give me this or that data. This is important because I said before that they are fine-tuned with evaluation from people, from experts, no? So the answer, I don't know, is never going to be the best answer, okay? So they are not, by nature, they are not accustomed to say, I don't know. You can tell them. If you don't know, tell me. Well, this has led to an entire field of research. Prompt engineering is an entire field of research on how to better interact with these models. Okay, some application. This is an experiment we did. This is a benchmark workshop. This is a conference organized by the ICOL in which problems are posed to the participants, in this case for predicting dam behavior, something we have been speaking about for this morning. So here we had 6 different variables over 2 different periods. So in total, 12 scenarios for accompanying, pressure, displacement, etc. And 2 time periods. First, during the training, the contributors, the participants had the inputs and the response. And in the last period, they only had the inputs and they had to provide the predictions. No? So what we did to test these models was to these are the 18 teams participating in this event all over the world. Only 6 of them provided solutions for all the variables. Let's say it's not so easy task with different approaches that you can see here on the right: analytical, finite element method, machine learning, etc. So we created something like a custom GPT, provided some specific instructions, and gave, you can see on the left bottom, the PDF with the problem, instructions, and the files with the data. The same information that was provided to the participants. And asked the model to compute the predictions. That's it. Every time it asks, should I use this algorithm or the other? We said, do what you think is best. That was it. So what these models do is to actually write code. And this is important because you can go and check and read the code and verify if the code is correct. If you have the capability for that. But you can access what the predictions are based on. And of course, we can compare the accuracy, the prediction versus the observations. This is the 12 scenarios I mentioned before. We have the average of participants in the center, the best participant, and our custom GPT. And this is accuracy, mean absolute error for each variable. In all scenarios but one, GPT was the best than the average of participants. And in 2 of the scenarios, it was even better than the best participant. In a matter of minutes, go compute the predictions, give me the predictions, I can compare them with. So highly accurate, I can say. But second step was to interpret the model. Tell me about the dam safety, analyze the results, interpret the model. No, remember we spoke about that when we spoke about digital twins, right? Well, the answer was not so good. In particular, the model identified a downstream shift, 7.5 millimeters. This is not right. This is wrong. And we asked, and we found that this is wrong because it used a method that doesn't make sense. Now, just compare the average over 2 different periods, and since there was a difference in average, we said, well, there's a downstream shift. This is wrong, in summary. Another test that we did was to reproduce the same again. We said there is some random component. So what if we run again the same experiment? Well, the approach was totally different. It used a different approach, an analytical model. The accuracy was much lower, but the interpretation was better. The structure is stable dam, no progressive loss of stiffness, good. So there is some randomness, and we have to consider that. And another feature of these models is that they improve very, very fast. Maybe you have heard about Claude and this Fable 5 model. It was announced like a breakthrough, something different, amazing, etc. And so we made the same experiment with this model. And the accuracy, I didn't show them, are similar to ChatGPT, more or less. But the interpretation is much better, I have to say. Yeah? For both pendulums, the time effect is small. It actually computes the time effect and the star reversible behavior and everything. So we found an improvement in terms of interpretation, not so much about accuracy. Another application, this is a digital twin, our finite element model. This is the kind of output that we are getting. We want to interpret, to draw conclusions, engineering variables from this output. So we try to generate a software application to post-process these files. So this is the code that the ChatGPT generated. Again, you can verify, but it's very long code, so it's not that easy. So in this case, it's quite better to use one of these software development environments. This is Visual Studio Code. You have here on the right your assistant and your script on the center, and you can better improve your code with this kind of tools. But we ended up with some nice software application when we can upload our files and do sensitivity analysis, stress distribution, etc., based on the results of our field. So to conclude, well, these models should be treated, in my opinion, as a very fast junior engineer. Someone who has read a lot about like everything and remembers like everything, knows how to reason, but doesn't have a lot of experience. Can work overnight, no problem. Is too kind sometimes, so be careful. Wants to be kind with you, and sometimes just invents. But in terms of coding, it's amazing. The best way of using it in general is to provide constraints, guardrails, do this, don't do that. Retrieve information. This is the particular information I want you to focus on. Forget everything else. And verify. Verification is essential, and it's the main point in our perspective. We have to use it with care. The responsibility is yours. Someone said at the beginning that maybe in the future or artificial intelligence is going to make decisions. I'm not fully sure about that. Maybe we can discuss it afterwards. Because of this, because no OpenAI, no Anthropic is going to say, I am responsible for your decision based on my output. No, you are going to be responsible. So it's your responsibility to verify that the output is correct or not. You are going to sign this safety report or whatever. Not because they're not going to be powerful or skillful, but because the responsibility is going to be always on our side, okay? In another note, you will never make a strong or important decision in your company from the information given by the last engineer at the office, right? You would always verify it before making a relevant decision. So our engineering knowledge is still essential, and this maybe proves it. This is a chart very recent from The Economist on the change in employability of different professionals in the States in the last 2-3 years. Civil engineering, we are on the safe side, let's say, less exposed to AI, you can see in the bottom. So there has not been a big change in employability. On the right-hand side, on the risky side, we have computer scientists, for example, more exposed to AI, and they have experienced this decrease in employability. Not sure if this is a general trend, but these are facts. So where should we go? This, at least in our opinion, we have spoken about limitations. Well, I think this is the way to go, and this is the way we're going, to develop agents. Agents based on LLMs have an LLM, a model of this kind at the core, but they are connected to external tools that we spoke about before, FEM models, machine learning predictive models, engineering reports, manuals, books, our information. These tools can be verified by us. We know they work well. So the agent, the LLM, its only or main mission is to decide whether to call to one of these tools, send the data, get the answer, and put it together with this engineering knowledge to provide an answer. But the answer is based on evidence. You can read that at the bottom. Hopefully nothing invented. Still, you have to take care and verify. But hopefully this reduces hallucinations. If what this is done with function calling or MCP is a modern context protocol, a little bit of technology out there, but I think this is the right way to go. Even more if you can do it locally without having to send your data out of your premises. So this is all just a very brief conclusions. Verification, again, is essential. I want to emphasize that. It's important to mention that it's very difficult to define benchmarks. When you want to compare one version with the other of this new model, you need very well-developed benchmarks, and it's not an easy task to do. So it's more about test it and see if it works for you, verify, and see if it hallucinates a lot or not. And another issue, what reason? Geopolitics and log uncertainty can be an issue with these models. We have witnessed that last week. I don't know if you're up to date with this news, no? But this is the Fable 5 model I spoke about before. Great, the best one, and everyone was using it. And after some days, well, the US government forbid everyone but the US citizens to use this model. So what if you base your process, your workflow on these models, and suddenly something like this happens? Well, that's all. Thank you very much.
Thank you, Fernando, for accepting the invitation. It's all the things that I can say at this point. A very nice presentation. I think that it has opened our minds on the use of AI. And now we will have quick discussions. We have prepared a round table with some of the experts that have participated in the workshop today. So yes, maybe I can introduce the speakers, the participants in the round table. Jaime Flores from Canal de Isabel II, Deputy Director for Research and Innovation. From an engineering firms, we will have our alumni of the master, Luis Madruga, Head of Digitalization of AGESA. From Bentley, we will have Miguel Suarez. Of course, Fernando Salazar. It's our pleasure to have you as the point of, please take a seat. And we have an addition, we also would like to invite Carmen Marin from the World Infrastructure Forum. So she has been invited to bring the whole picture of infrastructure of what's going on because she is the executive director of a forum that is starting now here in Madrid. And I'm sure that she will bring a very nice broad picture of the evolution of digitalization, not just in the water infrastructure, but in general. So thank you all. I will stay here. I will pose the questions. Do they have a microphone or? Oh. Okay. So I will start with Jaime. We have been discussing about what a digital twin is. And we said, Fernando, for example, he told about Professor Lombardi and the analog models. I talk about the observational methods of Terzaghi. And I'm pretty sure that at Canal you have a SCADA system since many years ago. So the question is, do you think that there been a true and explosive revolution with these technologies that we call now digital twins? Or it's maybe an exaggerated buzz and it's just an evolution of the technologies and the practices that we already had? Hard question to start.
Now? Okay. Thank you, Ignacio. Interesting question. I think we are involved in a data-driven era or something like that. We are focused on purchasing sensors, installing sensors. Every day we have more and more information, more computing capabilities, velocity. But I think it's somehow exaggerated. I think changes are more gradual. In the case of Canal de Isabel II, we have an SCADA in our center of control since, I don't know, 30, 40 years ago. Maybe it was one of the first as SCADA in Spain, but we can make the most of every technology without a dramatic change. So in my opinion, it is something gradual. We are trying to use AI. Of course, we have a lot of examples, but it is not so recently. Since 2008, I think we were using neuronal networks for detecting the end users in domestic consumption. And anyway, I would say that it is a gradual change, and now it's somehow exaggerated to say that it is a revolution.
Okay. Any of the speakers can react, of course, if you want. If not, I will force Luis. I will re-ask the question from the point of view of someone that is working at a civil engineering firm. Let's think, what are the problems, the challenges that we find difficulties, or they were very intensive in effort required to be solved, that nowadays these data-based models or these digital twins will help. Yeah, so the low-hanging fruit is what I'm asking about. It's not working?
No, thank you. Yeah, so for as an engineering company, so we're based on design and construction basically. So what we've noticed is the acceleration, like it was mentioned before. So the data-centric approach that we're now taking also for managing construction, managing operations of assets. This has reinforced the need to manage better the information within our design processes. So processes like BIM methodology that was an effort for the last few years to implement across design. So these digital tools are now more and more important and are reinforced by this new focus on operation and management for decision making. So this has reinforced our capabilities and for us to work harder into giving more and better information in a digital platform for the next phases of the life cycle.
Okay. Yes, you're right. If we are thinking on, for example, when Canal started to bring water to the city of Madrid, for sure they didn't have the tools that we have nowadays. And I would like to ask Miguel Suarez from Bentley, because you presented a comprehensive view of the tools and what Luis said. What is the key advantages of this technology? It's the same question at the end. The modern technologies and more recently artificial intelligence, data-driven models can be to utility operation from your point of view as provider of software and integrated solutions for the management.
All right. So it's true that water utilities have been already supplying water for many decades, sometimes before computers, before internet, for technology. The context has been changing also significantly. So for what I've been hearing from all the interactions with water utilities, so the most knowledgeable people, they are starting to retire, and it's been difficult to replace people and getting engineers in this sector. So there is a workforce retirement heavy in this sector. So lack of human resources that typically the water utilities talk about. They are also under more pressure than before to be more and more efficient from stakeholders, from society, make sure that they are more efficient in terms of water losses, energy efficiency. So more than before. We also see that we are reaching a time where infrastructure, we start to have very old infrastructure in most cities. So a very big problem that will soon be happening. It's probably heavy investments will need to be made because a lot of systems already have decades and decades years old. So at some point they will start to fail if we don't replace it regularly. And I think that our investment in the sector is being below what is expected. So we are also facing that challenge. Furthermore, the stricter regulations than before, more transparency. Also the increased demanding, also because to feed all these AI data centers that are being built, they are very water intensive also. So all these challenges that are coming now more than before, that obliges utilities to manage, to deal with much more things to manage, and probably with less human resources. So I think that's here where this can be only possible with the support and usage of technology. So in order for them to do more than before and better than before, because they are mandated to do with less, because they have less human resources than before, I think that of course they need to rely on technology. And I think AI will help also doing this movement.
Okay. I think it's interesting to, although Fernando already said something about this, but to also understand the limitations of AI from a more deep scientific point of view. And so I would like to ask you, Fernando, to land a little the ideas that you presented in the talk. And for example, honestly, you know that I'm also have some knowledge of embankment dams. I'm a little skeptical because probably when we have some dams that has been that were built 50 or 100 years ago, maybe there are some processes that have not yet shown up, and maybe they will. So if we train with data in the past, the dam is a living object, let's say, this can be a source of hallucinations or whatever. No? So I would like to ask you again your point of view on these limitations.
Well, there are a number of limitations. That's one of them. I mean, that's probably more related to the previous models that we use, what we call machine learning models, no, where we just take the data and generate predictions. No, we typically train these models with healthy data, no, and when the dam is not healthy anymore, you have this problem. No, that's what you mean, right? What's really difficult, what all you can say when you find a deviation between the predictions of your model and what you're observing, you can say something is happening. But there, the engineers come into play to interpret that and say, well, why? What's the probable reason what this is happening? And then, of course, come into action and make decisions. But of course, you can try and simulate some anomalies, and maybe with a finite element model or something like that, and use that artificial data to feed these machine learning models. But we have done that in the past to try these different approaches to identify anomalies. But I would say that the anomaly you're going to have in your dam is never going to be, of course, exactly like the one you figured out, but probably not even close. So the usefulness of that approach is limited. So I would say, yes, you have an accurate model. You can predict very accurately. If you find a deviation, go and look for the most experienced engineer and try to figure out, maybe do some check, some verification, go on site, see if the device is broken or whatever. But limit the model to detect the anomaly. That's what I would do.
Interesting. And after having listened to these several perspectives, I would like to ask Carmen how the whole landscape is changing. You have administration, you have engineering firms, software providers, academia, all of them are talking about this evolution or revolution of the way in which we manage infrastructures, but probably this is also affected the entire landscape. Before that, as you didn't present today, I would like to ask you if you can explain a little bit what the World Infrastructure Forum is, and then we go with the question.
I'll try my best. So the World Infrastructure Forum is conceived as a platform, neutral and global at core, led by multilaterals and academia. Why is this? Actually, it's addressing one of the points that one of the colleagues were commenting just right now. We've reached a point in the history of infrastructure where a lot of different changes are converging at the same time. So the workforce, there's a problem in talent. There's lack of talent globally. It's not only here in Spain, but globally. There's also like a huge change in the digitization that is affecting every part of the value chain, not only decision-making or, prediction or like detection of things, but the whole value chain, even the production of the materials themselves, or robotics, like the vehicles that we are using, everything is being disrupted in every point of the value chain, right? So digitization is definitely a huge disruptor right now. Could be a huge opportunity, so not necessarily a challenge if taken, in the right angle. And then we have also climate is becoming slightly more unpredictable, or very much more unpredictable. We are going to be facing problems with water scarcity. We're going to, we kind of know it's becoming social discussion. It's not anymore a topic that only engineers are discussing, which is also one of the reasons why the World Infrastructure Forum is happening and why it's being given so much attention by so many huge stakeholders all across the globe right now, right? Because finally, at this point, infrastructure has become clear to be a vital part of people's life, which we kind of already knew it was always there, right? But I think it's becoming increasingly clear for everyone that quality of infrastructure, resilient infrastructure, climate-adapted infrastructure, human-centric infrastructure, it's vital for navigating the increasing geopolitical complexities that we're going to face, right? So these are all the reasons why the World Infrastructure Forum is happening. Like the conversation started with the head of MIT infrastructure and the director of Caminos, the engineering school here in Madrid. And they brought in the World Bank right away to the conversation because they thought, okay, we we have the academia, but we want the multilaterals as well to sit with us, and make this neutral and global, so that we can really convey in this environment of trust all the biggest players across all the sectors of infrastructure value chain, basically. So the WIF right now, like World Infrastructure Forum, is conveying not only engineering firms and construction companies, but also investors. So like Macquarie, Allianz GI, all these big companies that are to invest millions and millions, and not only on constructing new things, but also on maintenance, as is one of the huge challenges we are facing for sure. Insurers, because we are going to have to face a lot of different insecurity environments, uncertainty, like climate-wise, cybersecurity-wise. There's going to be a lot of different challenges there. So we also count with some of the biggest insurers in the world, like Swiss Re, like Liberty Mutual. So all these stakeholders are sitting, but not only. We of course have also like Google and big tech sitting for two sides of the coin. Actually, they are sitting because data centers as a physical asset is going to be something disrupting, and we are going to have to see how we interconnect them, I guess, with the whole network we already have in place, right? And on the other hand, AI, so the digital side of it and the physical side of it. So big part of the infra discussion worldwide and across all sectors. Yeah.
It's super interesting that you will have a lot of decision makers sit at the same table and discussing on digitalization, cybersecurity, and not just civil engineering firms. And let's talk a little about those decisions. Let's be more practical. And I would like to know from your different perspectives, for example, in the case of Canal de Isabel II, Jaime again, when you need to take a decision on digitalization, how do you identify those processes or solutions that will bring more added value for with a shorter investment, or are, again, low-hanging fruits?
Thank you. As a public company, as a public water utility, I would say that we are very, very careful about our investment. We start with a deep analysis about the proposal or the initiative, maybe a lab test, maybe a proof of concept or a pilot plant, and only a few cases when it has been really demonstrated that it's worthy, it's feasible, it's economically viable. Only in these cases leads to a larger scale implementation. Of course, the key factors are scalability, integration with the existing systems, sustainability. We are, as a public company, we are focused on our providing the best service to our citizens. In this case, this is how we prioritize the investment on these initiatives.
Okay.
And I will also say that the more important when we are talking about digitalization, and it has been mentioned already, is the key factor of the change management is crucial. People is used to do things in a way, and it is quite difficult to change their way of doing things. So in this sense, change management is crucial.
Yeah, that idea was also pointed out by your colleague. And I would like to ask Luis, because they have maybe the problem twice, because they have clients and they have internal teams. And as you said, the engagement of the people and the teams is really important to make digitalization possible. So how do you deal with this, Luis, as you are heading the digitalization department at AGESA?
Yeah. So that's the hitting the nail on with the hammer. It's because it really is the critical point for the last few years. I've been involved in implementing BIM for a few years now, and it's the reluctancy to accept change, to change the processes that people are used to. But we have well, within my within our company, where I'm a digital engineering team in an engineering company, and we're the special ones, the ones that do things that many people don't understand why we're doing it. But we've noticed a change in the last couple of years. What I associate with is the availability of tools like the AI, and everybody's using this new technology. So, and it's moving very fast. So everybody now from everywhere is using new technology in the digital platforms. And I think this has shifted a little bit the mentality also internally, because now we have a lot of colleagues that come to us and ask, how can I improve this? How can we create a tool that we can optimize our automatization for the processes? So I think the barrier, it's shifted a little bit, and now it's more like okay, yes, this is this is possible, but it's more managing expectations, because they see AI, ChatGPT doing a lot of great things, but those need to be carefully studied to implement in an engineering process, like it's been demonstrated. So that's the biggest challenge now. Is saying, how do these tools are great, they're improvements, but how are we going to implement them internally to do it correctly? And for our clients, it's more or less the same thing. Some of them are demanding a lot of things, and that represent also challenges, not only of what is the capability of, or what is responsible to do with these types of technologies, but also what is required from the infrastructures that are available, especially in public institutions that are not so big, like Canal Isabel II is a very important institution, but to smaller organizations that are more limited in this way. This is also a challenge, but yeah.
Okay. Thank you. And let's go deep in the management of the expectations. And by the end of 2022, ChatGPT was released to the general public. Fernando, you have shown a lot of LLMs. The question is for Bentley, because you are providing solutions for our clients that that every year the picture has changed totally. Many processes that require a lot of effort has been replaced by automatic tools. So how can you not lose the pace and offer tools that find a compromise between the easiness to use, the reliability and the capacities, and also that are up to date in this world changing so fast?
Yes. So as a provider of software, Bentley, so we serve several industries, not only water, and we have seen this quick movement from more automation, more AI, also from our users, probably starting more on other sectors, but now starting to reach water. But first, internally, there are been already several significant changes at Bentley, specifically because right now we are already noticing, and we are already testing by ourselves, and we are really experimenting, and we are already shipping and developing features much faster than before, and some of them using AI agents to do those features. So even internally as a software provider, we are also benefiting from AI, because we are already developing with AI also our internal tools. So we are shipping much faster, developing much faster. So this is one thing. To put value on our users. So what we hear from our users and their expectations. So they expect more and more that they have these conversational interfaces instead of navigating through the different dashboards, to the multiple pages. They are already expecting that they can just throw a question, get an answer, or immediately be notified by something without needing to drill into all the dashboards. So they are already expecting this much faster interaction to these agents. They want, of course, their workflows to be automatized, because there is a lot of manual iterative workflow also in the water industry. And we are also already developing these AI chat agents. We are also already automatizing a lot of the tasks, even for manual design, manual pipe size, automatic design, automatic pipe sizing, drawings, automatic drawing, saving already a lot of hours to our users. But I also agree with when you said that this is changing fast. We see this in Bentley, that every month, every 3 months, every 6 months, we can ship faster new things, and we see users starting to use it much quick. So I think this will evolve even faster in the upcoming months and years. I think in our sector specifically, because we are managing critical infrastructure, water systems, even buildings, road, bridge, so civil engineering, and also this was addressed in the last presentation. I don't think that AI will come to a point where that will replace humans. We Bentley really strong believe that we have this phrase that is human in the loop. So we really believe that at the end, human needs to validate, needs to acknowledge, and final decision needs to be to the human, not to the AI, because maybe in other industries, consumer services, that's possible, but in critical infrastructure, a small failure means probably people will die, right? So I think that AI will be here to help us be more efficient, help us to be more, probably invest smarter, decide faster, decide better, but will not replace us.
Yeah. Okay, that's the idea about the accountability and responsibility.
Yes. So on that, good. Yeah, on that part. So we have been moving faster and developing faster, but as software provider that we developed software for these critical infrastructures, we always need to keep in mind the reliability part, the performance part, stability part, the secure part. So we can't sacrifice the reliability, the performance, the stability of our products and benefit to be faster. So we need to make sure that we handle both of the best world, let's say like this. So if you would ask me some years ago if it's possible to conciliate to be fast and at the same time precise, with precision, reliable, stable, probably some years ago I would answer you have to choose one, or you are fast and probably not so precise, or if you want to be very, very precise, you can't move so fast. But now with AI again, and because we are leveraging also AI to develop, we are also freeing up our human resources, our developers, to focus on other activities. So we already have parts of the code that is being done by AI agents. So that's time that we are freeing up from our resources. They can put also now on the security part, on the validation, on the reliability. So we can really conciliate now moving fast with precision. So we have a mandate from above, from our CEO and CTO, that is move fast and with precision. So then that's, I think, what we are doing right now also in Bentley.
Okay. And talking about this, first, Fernando, I have changed the question because the question that we have planned has been already said. So I would like to ask you as a researcher, now you have capabilities to try ideas faster, see results faster. I'm really scared about the idea that we can publish more with these tools because maybe we need to stop at some point. But the idea of trying new ideas, how is disrupting your work as researcher with these new tools? Because I imagine that every day you wake up with a new idea, and what before you need maybe months or years, you can try in weeks or days. So that is totally disrupting your.
Yes, well, that's. No, okay. I think that yeah, it helps a lot in exploring the landscape of the publications. You say there's an inflation of publications. You just can't keep track of everything that's published, even in your very field. So these tools can be really helpful for that. And I am relating this with what Miguel said before, and I also before. I mean, this is a task, reviewing bibliography, in which if you lose one or two papers, there's not a big problem. If you are managing critical infrastructures, that's not the case, no? So I would say that yes, with these tools, tasks that are not very critical can be improved by a lot, no? So yes, in this particular area, it's very useful. About writing papers, that's another topic that we could be speaking about maybe for hours. Mm-hmm. My personal experience is that I haven't used these tools for the moment for that, but there is a nuance there. The line is very thin. I mean, what I typically do when I write a journal paper is to write it in Spanish, because it's more natural for me and that my ideas come at the same path as my writing. No, if I try to do it in English, it's slower. No, so I typically write it in Spanish and then I go and translate. So what is the difference between doing that with some translator and doing it with some AI? Mm-hmm. I think that the line is very thin. So my ideas are there. I wrote the original manuscript, let's say. I think AI is better for that than a conventional translator. So there's an open debate. You know it for sure in the academia on that. And yes, unfortunately I think that this is leading to even more papers of lower quality being published. That's a big topic. I think not so inside the frame of this event.
Okay. Probably. So in this world that moves faster, we need guidelines. We need, and my last question is again for Carmen, because we have been talking that when Canal started, it was 175 years ago. Many of the tools that we have today didn't exist. Even when most of the dams were these large dams were designed and built, they didn't exist. Many in this room lived when internet started, the smartphone started, AI, now we are living this revolution. But the WIF is a digital native forum. And maybe it's a difficult question, but I would like to dream, what will it happen if this forum were organized in 20 years from now? Maybe just AI agents are discussing on the future of infrastructures, or how it will be?
I mean, yeah, it's a tricky question for sure, because I mean, it's hard to imagine what it's going to be in 20 years. We cannot really tell. I mean, no one would have guessed 25 years ago where we are at right now, right? So we don't even need to think of 50 years. No, 20 years, who knows, right? I mean, we are already seeing like the trends, right? So the trends are going to be about physical automation and digital automation. So that is definitely going to be there. I believe the future of work itself is probably going to be challenged. I don't think there's going to be employment for all the people that exist. So I guess infrastructure systems and infrastructure as a sector is going to be as well completely challenged by the fact that much of the work is going to be done by algorithms and machines that move by themselves. But I do agree with you that the ultimate decisions are going to have to still be made by humans, because there's a huge accountability in this sector. So, I mean, probably not all of them, not all the time, but ultimately, I think infrastructure sector is going to be one of the last, if ever, to get rid completely of human accountability. I mean, I might be wrong, obviously, who knows, no? But that's what I'm feeling. And the thing is, I believe the challenge is going to move, let's say, to higher spheres. So it's not, I mean, in 20 years from now, it's not going to be anymore so much about how much data we can gather or what's the quality of that data. For sure, those challenges will be by then solved. But I mean, security, cybersecurity, etc., will always be a problem, probably, but not only. Like, what you do with those data, I mean, the decision-making process with all that knowledge, that's going to be the problem. So I think it's going to be more on governance than on technical side of things. That, I mean, we are going to start seeing like countries, well, the same as happens with water, right? So if you have the source of the water in your territory, you have a power that is clear, right? Well, if you happen to have access to whatever knowledge data-wise, you also have insane amount of power, right? So we believe it's going to be moving in that direction, like governance. And then the thing is, we might be looking at the concept of infrastructure, I mean, from our restrictive minds, right? So we are thinking of optimization, we are thinking of automation, but probably what will happen in 20 years from now is that the way we think about infrastructure will just change completely. So it will be radically different. So it's hard to imagine in which way, right? But for sure. Yeah.
Okay, thank you very much. I would like to thank all the participants of the roundtable. Does any of you dare to summarize with one sentence? I forgot to ask you to prepare this ending. So if not, I think that, no? Okay.
We can try, we can try.
No, I was about to say that maybe in 20 years, our digital twins will be here discussing, yeah, what it means.
No, I'm just saying that clearly things are moving faster, as everyone said here, right? So I would say that there is a global agreement that we own to the people to make infrastructure not only more resilient and more sustainable, but also smarter. So yeah, let's do it.
It's a sentence to take away. Digitalization, AI just helps. We are also useful.
Yeah. Okay.
Yeah, no, if I want also, if I need to summarize, I think it's so the key is people, right? Because digital twins and technology and AI will be used if people also open the space and also adopt it and have a mandate to that and to do that. And I also think, as we talk about that, at the end, I think they are here. They are already here. They are already here. We cannot run away from them. So we will need to use them. I think they will just help us to be better and more efficient. And I think they will not end up to replace, at least in this critical infrastructures sector.
Yeah. Better tools, better decisions.
Okay, good. Okay, thank you so much. I will end with 2 sentences. One is please enroll in the master program. No, the second is a big thanks to all the speakers, the participants in the roundtable, all the presenters, the cases brought by our guest administration Canal de Isabel II, and also the support of Bentley, all the people attending, discussing in the networking events, and also the people that are following us on internet. So thank you very much to all of you. Juan, ¿quieres añadir algo?
No, solo agradecer la oportunidad de despediros a todos. Creo que ha resultado muy interesante todas las charlas, los pensamientos en común que tenemos y alguna que otra falta, digamos, de unidad en algún pensamiento, porque bueno, todos somos libres, ¿no?, de pensar lo que queramos. A mí, si me hubieras preguntado qué frase diría hoy, te hubiera dicho ask to my digital twin. Y con eso digo todo. Quiero decir, yo sí soy un profundo optimista sobre el uso no hoy, pero sí en el futuro de los gemelos digitales, un uso responsable, evidentemente, y que nos ayude a investigar en otros asuntos. Gracias a todos y espero que lo hayáis pasado muy bien. Gracias.